Alright students, so here we are with the test 1.1 review. Now, if you take a look in the bottom right of the screen, you will see the timestamp as 11:04 p.m. And I thought I would just briefly explain this as I prepare to do the review. I came home from school with the full intention of doing this review, and then I immediately fell asleep, and I just woke up about 45 minutes ago, which was probably a bad move since now I'll be awake all night. But the flip side is, the upside is, I've got time to do this review, so I'm going to try to do this in one take. I'm going to start with number 1, and because I've already gone through this whole long discourse that's available separately as a video, I'm just going to compute and prove the inverse as you would do on the test without any extra fluff. And then I'll just continue to proceed all the way through the test in kind of a direct way. If you have any questions about this, reach out to me via Canvas, through email, parent phone call, remind, etc. Send a messenger pigeon. Otherwise, let's dive in, and we're going to do number 1 again, and I'm just going to show the direct solution. So remember how I do this. I clip out the question. Let me just clip it out and copy it, and then find some blank space on the page. In this case, we'll try to keep it more or less over here. Paste it here, and let me just go through it. So we can assume that these are both functions. Remember, that's a prerequisite for evaluating whether the two functions are inverses. First, they have to both be functions. So we can just assume for now that they are functions. We already know that they're functions based on this Desmos graph over here. But here's how you would prove that, okay? What you're going to do is you want to show that if you plug in f of x into h of x, where you see the x, and you evaluate that function, you simplify that down, and you get x. And then if you do the reverse and you plug h of x into f of x, where you see the x right here, and you get x after reducing, simplifying, etc., then you've proven that the two functions are inverses of one another. So here's how that looks. H of f of x equals -10 plus 4 big parentheses f of x close parentheses, and then we need a straight edge because we got to make a big fraction bar, all over 5. So I've plugged f of x in where the x was in the function h of x. And now I'm going to substitute 5x plus 10 over 4 for f of x. So h of f of x equals -10 plus 4 open parentheses. And now I'm going to actually put all of this. 5x plus 10 over 4 close parentheses, big fraction bar here, all over 5. All over 5. Okay, so the first thing I want to zoom in on is this section right here. Okay, because that's where we have to start. PEMDAS, parentheses, exponents, multiplication, addition, division, addition, subtraction, states that we start with the parentheses. And I just want to highlight here over in side work that when I distribute this 4 to this fraction here, one of the things I'm doing is I'm distributing a 4 over 1, that's this 4, to some fraction, okay, with a numerator but a denominator of 4, okay? That fraction up there is 5x plus 10, but here's the point. Those two 4's will cancel out. So over here, I can just cancel those 4's out. That's going to help us a lot to simplify this. H of f of x equals negative 10, all the parentheses are gone now, plus 5x plus 10 all over 5. Now let's notice something. Negative 10 and positive 10 equals 0. So those cancel out. So now I have h of f of x equals 5x over 5. Those 5 cancel out, leaving us h of f of x equals x. And this is the first of two things we have to prove in order to prove that the two functions are inverses of one another. So let's go ahead and box that. That is step 1, okay? So this was thing 1 that we had to prove, okay? So we proved it. Now here's thing 2 that we have to prove. So let's call this part A. This is part B. It's basically the reverse of what we just did. Instead of doing h of f of x, we'll do f of h of x. F of h of x is equal to, now we take the basic framework of f of x here, and we're going to start with 5 open parentheses, and then here I'm going to write h of x, close parentheses, plus 10, big fraction bar, denominator is going to be 4, okay? So now we're going to substitute h of x, which is negative 10 plus 4x over 5, in the parentheses where we see h of x. So we're going to write f of h of x equals 5. Big open parentheses. Now we're going to put the full h of x in there, negative 10 plus 4x over 5, negative 10 plus 4x fraction bar over 5, close parentheses, plus 10, bigger fraction bar, all over 4. All right, proceeding along, we got the same situation here that we did up here, okay? Those cancel. So I can cancel the 5's. That's going to really simplify what we have to do because it got rid of the fraction, or the top fraction in the numerator. F of h of x equals, drop all the parentheses now, negative 10 plus 4x plus 10 all over 4. Now notice something. Negative 10 plus 10 is 0. Cancel, cancel. So f of h of x equals 4x over 4. And those 4's cancel, leaving us f of h of x equals x. Bingo. So that was the second thing we had to prove. So let's bring these two things together just to write it down. Here's the proof that h of x and f of x are inverse functions. h of x and f of x are inverses because of rule 5 from your worksheet, are inverses. Why? Because f of h of x equals h of f of x equals x. They all, because f of h of x equals x and h of f of x equals x. Therefore, the definition was that was the definition, proving that the two functions were inverses of one another. You're done. Done with number 1. Moving on to number 2. Now, number 2 is going to get complicated. All right. There's a song from when it's come out, 2001 or 2002, called "Complicated" or "It's Complicated" by Avril Lavigne. And that's how this problem is. It's a little bit complicated. So let's go find some space to work out problem number 2. So I want to kind of keep these roughly in the same vicinity of one another. So I guess I'm going to put it over here. So problem number 2. So let's try G. This is going to be part A. G of f of x. Now let's see if we can reduce this down to x. G of f of x equals negative 7/5 open parentheses f of x close parentheses minus 18/5. Now, there's something about the right side of this fraction that I think we should fix. Okay? This is written in slope-intercept form, and you've got 5s in the denominators of both the terms separated by a minus sign here. You could rewrite this like this: G of f of x equals negative 7 open parentheses f of x close parentheses minus 18, and then you could just put all of that over 5 like this. So just want to point something out. This and this are exactly the same thing, just written a different way. Take a look at the two of them and see what I did. Okay, they share the denominator of 5. So that's what I did in the second. I just made it to where the denominator existed beneath the whole numerator. And I did that to just try to simplify, because it's already complicated enough. So now we're actually going to perform the substitution. G of f of x equals negative 7 open parentheses. Now we're going to put in the whole thing, 15 plus 8x over 5. 15 plus 8x over 5 minus 18, and remember the big denominator is 5. I'm going to make sure that looks like a 5. Okay. Now, remember last time and the time before these two cancel. Well, this time they don't cancel. So that's kind of like your first clue that something is wrong. If you start to look at these numbers, you start to see that unless something really magical happens, we're going to have a problem. But let's go through it together and actually see that problem develop, because they wanted us to skip this one, but if we skip it, then we don't learn why it's hard. Okay, so here's what we're going to do. We are going to distribute multiply this negative 7 to this 15 and this negative 7 to this 8x, and we're going to see what we get. So over here in side work, we're going to multiply 15 times 7, since I have no idea what that equals off the top of my head. The result's going to be negative since it's negative 7. 5 times 7 is 35. Carry the 3. 1 plus 7, or 1 times 7 is 7, plus 3 is 10, so negative 105. So here we go on top. We got negative 105. And now negative 7 times 8x is minus 56x. All over 5. Minus 18. The whole thing over 5. Okay. So now it might be good to rewrite this huge denominator of 5 and split it back up among the terms of the numerator. So in order to do that, it's important that we group this as a fraction. So let me go ahead and write that step. G of f of x equals, open parentheses, negative 105 minus 56x over 5 minus 18. And then each one of these is going to get its own denominator of 5. So this is going to get a denominator of 5. And this is going to get a denominator of 5. So we have this. Yeah. Here's the problem. We have, in this situation, well, we'll focus on one thing and then we'll come to a conclusion. So let's focus in just for a minute on what's going on here. So this is like a compound fraction. It looks complicated. It isn't. If we write out what is happening, then it will be a little bit easier to understand. It's not going to help us get to the conclusion, but it's something we need to go over. So again, side work. We have negative 105 minus 56x over 5. And it's good to write this out, divided by 5 over 1. That's what the fraction bar means. The fraction bar means division. Okay, so we don't divide fractions, we multiply by their reciprocals. So this is equal to negative 105 minus 56x over 5 times 1 over 5. So this is why I said it doesn't help us, it just makes it even worse. So this equals negative 105 minus 56x over 25, right? Because you multiply the top times the top and the bottom times the bottom. 25. Now let's notice something. While 5 is a common factor of 105 and 25, 5 is not a common factor of 56 and 25. So the factors of 56 are 7 and 8. The factors of 8 are 2 and 4. The factors of 4 are 2 and 2. So if you prime factor 56, you get 7, 2, 2, 2. If you prime factor 105, you get 3, 5, 7. If you prime factor 25, you get 5, 5. So unfortunately, there's no common factors between 56 and the other two numbers. We call that irreducible. Okay. Further, there are no common factors between 18 and 5. So break down 18, 6 times 3, break down 6, 3 times 2. So you have got the prime factorization of 18 is 2 times 3 times 3. The prime factorization of 5 is 1 and 5 because 5 is prime. So there are no common factors there either. So we've reached irreducible complexity. Okay? Or irreducible simplicity, I should say. Here's the point that I need to make, okay? Just I'm going to put this out there. This does not equal x. Remember the rule, g of f of x has to equal x. Now, actually, you know what? I'm going to do it. I'm going to do the other thing, right? So part A failed. Now that means the whole thing's going to fail, but let's show part B because I want you to see what it looks like for a problem to not be an inverse. As I was saying in class, this seems like a lot of work to prove something that is going to be a no. But in mathematics, we should be indifferent to whether something is true or false. We should just be sort of seekers after the truth, like the validity. So we're sort of indifferent about whether it's true or false, that these are inverses. We're really just interested in proving one or the other, regardless of the outcome. So f of g of x is 15 plus 8, open parentheses, g of x, all over 5. Okay? And so now we're going to substitute in what g of x is. So f of g of x equals 15 plus 8, big parentheses here. And now g of x is negative 7. I'm going to use this form here. I'm sorry, not that form. Where'd it go? This form here, this one here, where I put it all over the same fraction. Okay? This is what I'm going to stick in there. G of x. Remember when I took this and I wrote it as negative 7x minus 18 over 5. And I said that that was equivalent. So g of x equals negative 7/5 x minus 18/5 is the same thing as saying g of x equals negative 7x minus 18 over 5. Okay, so negative 7x minus 18 over 5 okay, and then all of that over 5. So let's do the work. We're going to distribute that 8 to the negative 7x and to the negative 18. So f of g of x equals 15. And then 8 times negative 7x. So I need to put inside work. 8 times negative 7x equals negative 56x. So I'll go ahead and put a plus here. We're going to leave this as a fraction. Up on top, I've got negative 56x. And then I have no idea what negative 18 times 8 is. So let's see, 18 times 8. 8 times 8 is 64. Carry the 6. 1 times 8 is 8, plus 6 is 14, so that's 144. And that's going to be minus 144 all over 5. Close parentheses. And then the whole numerator all over 5. Okay. So I mentioned in class, one thing we could do that would help simplify what the task at hand is to make a common denominator between negative 56x minus 144 over 5 and 15. So over in side work, I would like to just point out that 75 over 5 is equal to 15. Why? Because if I take 75 and I divide by 5, I get 15. Okay? So 75 fifths is equivalent to 15. And if I write it that way, if you'll forgive me here, I'm just going to scribble, all right? If I write that like 75 fifths, I then have in the numerator a common denominator. And I can combine all of it and drop the parentheses, all right? And that's just going to, just watch it happen. It's going to make it look a little bit more clear. We're really just playing algebra tricks now. So I got 75 minus 56x minus 144. The whole thing over 5. And remember, there's this huge fraction bar underneath it divided by 5. So I'm going to write divide by 5 over 1. Because that's what we're doing. We're taking this whole numerator, okay, all of this, and we're dividing by 5. So this whole thing is divided by 5. So that's what I've written here, but I've written it using the division symbol. And that's because I want to rewrite this as a multiplication by the reciprocal. Just to prove a point, all right? So now f of g of x equals 75 minus 56x minus 144 and then 5. So that was times 1 on top, so it just stayed the same. And then on the bottom, the denominator actually becomes 25. Okay. So here's the problem. 75 and 25 have common factors, namely 25, right? You could divide both by 25. 75 divided by 25 is 3. 25 divided by 25 is 1. But I can't divide 56 by 25 or any of its factors. I feel like doing this. So I'm going to prime factor everything you see here and just show you the problem. Okay? Why is this failing? Here's why. What do I mean by prime factor? Okay, here are the prime numbers. 2, 3, 5, 7, not 9, 11, 13, 17, 19, 23, etc. Okay? So when I say prime factor, I mean break these numbers down into these numbers. So 75 is 25 times 3, and 25 is 5 times 5. So I can rewrite this as 5 times 5 times 3, right? Minus, and then 56, 7 times 8. 8's 2 times 2 times 2. So 7 is a prime number, right? And 2 is a prime number. So this is minus 2 times 2 times 2 times 7 x minus 144, which is 12 times 12. Now 12 is 3 times 4, and 4 is 2 times 2. So 12 times 12 is 3 times 2 times 2 times 3 times 2 times 2, which is really 3 times 3 times 2 times 2 times 2 times 2. Okay. I promise there's a point emerging. What is 25? Prime factored is 5 times 5. Now, this is the point. So in order to reduce this fraction, you would have to see a 5 here, which we don't see. And you'd also have to see a 5 here, which we don't see. We further see nothing that we can pull out of all three terms of the numerator. All right? So I see I could pull a 3 out here and a 3 out here. I could pull a 2 out here. I could pull 3 2's out here and 3 2's out here. But I can't pull anything out of this. There's no common prime factors. That's what I'm getting at. And so this is fully factored, right? This is simplified right here. And the thing that I want to point out is that this does not equal x. And so your solution to problem 2 is kind of it seems like a disappointment, right? So here's the conclusion. See how they listed g of x and f of x. Here's the conclusion you want to come to. G of x and f of x are not inverses. Okay? Why? Because g of f of x does not equal f of g of x, which does not equal x. So the thing you would write up here, back at, let's go all the way back to the paper, is no. So there is so much work involved to say no. All right, let's move on to number 3. Let me clip this out. Yeah, they said skip that one, but I wanted to show it because I wanted to show what does it look like when it goes wrong. You know, what does it look like when the algebra gets really, really hairy, okay? Really challenging. Let me put number 3 here. Okay. So, let's do part A. Not with red. Part A. Part A is going to be g of f of x. So that's going to equal negative 3, open parentheses, f of x, close parentheses, minus 3. And now let's perform the substitution. G of f of x equals negative 3, open parentheses. And now we're going to stick this whole thing in there. So we're going to write negative 1/3 x minus, and if you'll permit me, well, no, I don't want to confuse people, minus 1. So I've just put this in there, right? Close parentheses, minus 3. And now I'd like to ask you if you will permit me. So, if you will permit me to take a look at the number 1 for just a moment. And let's pull up a little side work here. Ladies and gentlemen, brothers and sisters, do we all agree that 1 is equal to 3 over 3? Yes? Okay, now there's a reason I would write it like that. So let's rewrite this like this. G of f of x equals negative 3, open parentheses, negative 1 over 3x minus 3 over 3, close parentheses, minus 3. And now remember what I said before. Inside the parentheses here, we've got denominators that are identical, so we can combine them as a single denominator. So on top, I'm going to have negative 1x minus 3 all over 3. Okay? G, just watch. G of f of x, there's a point to this, equals negative 3, open parentheses, and I don't need to write the 1, so just negative x minus 3 all over 3, close parentheses, minus 3. Now, I need to further ask a question, if I may. Can we all agree that negative 3 is really negative 1 times positive 3? Can we agree? Yes? Are we all in agreement? So let's write that. G of f of x equals negative 1 times 3, open parentheses, negative x minus 3 over 3, close parentheses, minus 3. Now you're about to see the fruits of your labor, ladies and gentlemen. Oh, whew. So, we got a 3 here, which is a numerator 3, and a 3 here, which is a denominator 3. So we got a numerator and we got a denominator that are identical. Guess what that means? We can cancel them. And that's why I did what I did. Okay? So that there was a point. There was a reason. There was a reason for the season. So now let's do g of f of x equals -1. Don't forget about that -1. Times -x minus 3, close parentheses, minus 3. Now let's distribute that -1, which is really just another way of saying change the signs inside the parentheses. Okay? That's what the effect of multiplying by -1 is. So let's write g of f of x equals, well, -1 times -x is just x. -1 times -3 is +3. And then don't forget about this guy here, minus 3. Now do you see that beautiful thing that's about to happen? What is 3 minus 3? 0. Okay? So g of f of x equals x. Wow. Thunderous applause. This was part A of the thing we had to prove. Remember, we have to prove that g of f of x equals f of g of x equals x. Well, we proved that g of f of x equals x. Now let's see if we can prove that f of g of x also equals x. And if we can do that, we know they're inverses. So now we're going to do part B, which is to prove that f of g of x equals x. So f of g of x, let's go find out what it is. F of g of x. So I'm going to write -1/3, open parentheses, g of x minus 1. Okay? -1/3, open parentheses. I'm doubting myself. G of x, yeah, minus 1. G of x minus 1. Okay. So now we're going to perform the whole substitution. F of g of x equals -1/3, open parentheses, and now g of x is -3x minus 3. So we're going to write -3x minus 3 minus 1. Okay? So now what we're going to do is we are going to distribute this -1/3 through both terms of the parenthetical expression. So we have f of g of x equals, now -1/3 times -3, you multiply the -1 times the -3, you get +3 over 3. So we have 3/3 x, and then we have -1 times -3, that's +3 over 3. And then we have minus 1. Okay. Now we see here that these cancel, leaving behind 1s, and these cancel, leaving behind 1s. So f of g of x equals x plus 1 minus 1. 1 minus 1 is 0. So, yay, f of g of x equals x. And we'll put that in the red box of correctness. Thank you, Jay, if you're watching. Bingo. Okay, so let's bring together our two conclusions. So here's our conclusion. G of x and f of x are inverses. Okay, why? Because g of f of x equals f of g of x equals x. IMHO, in my humble opinion, this is just as important as all of the algebra that's above it. Okay, so that would be the work for number 3. Welcome to Algebra 2, folks. It's more work than Algebra 1, but I find this fascinating. And I won't do too many Morelli digressions here, but there are two types of people on Earth. One of them enjoys this. The other person hates it with a passion. Now, I happen to love this, okay? I just absolutely love doing this algebra. And that's probably why I'm teaching algebra, right? Because this is just super fun for me. I love lining up the equal signs. I love the organization. I love the simplification. And I love finding these little tricks and conclusions and noticing the 3's are going to distribute and then just get all excited about it. Okay. Now, there's a whole separate supermajority of human beings who are doing this and they literally want to claw out their own eyes. Okay. Like they hate it. I mean, I have family members that fall into this category. That's why I'm laughing. So here's the thing. If you are one of those folks that just hate this, I'm with you. I used to be one. You know, and I'll tell you, it's just, I just didn't understand it. And so my goal as a teacher is to try to help you understand and appreciate that this is art. Okay? It's like penmanship or something. You know how penmanship can be artistic? This is art to me. This is beautiful mathematical art. So if you can try to look at it through that lens, maybe it'll be a little bit less burdensome. But I can tell you, I do understand and I sympathize with those who just hate this. It will be over soon, and I'll try to make it as fun as possible and supplement your misery with candy and the occasional fun game that we will play in class. Okay? This seems like a good place to take a little break. I'm exhausted. We've been working for about an hour, right? So we'll pick this back up with number 4 here in a minute. See you then. Okay, students, we are back, and we are moving on to number 4. So keen observers of the timestamp will note that that little break that for you took about 1 second, took me a couple hours. But a promise is a promise, so we will continue fighting on. So we're here on number 4, and we're going to try to determine if these two functions are inverses of each other. So let's clip it. And find a place to paste it. Where should I paste it? Should I go further or should I go down? Let's put it right here. There we go. All right, zooming in. Here are our two functions, and what we're going to do, ladies and gentlemen, is we are going to try part A, which is, if you recall, to do f of g of x and see if we get x. So f of g of x equals so we're going to write the 6 and then an open parentheses, and then we're going to put g of x where that x was, close the parentheses, and then put plus 4. Okay, and now we're going to substitute 1/6x minus 2/3 where that g of x is. So f of g of x equals 6 open parentheses, and then here we're going to write 1/6 x minus 2/3, close parentheses, plus 4. And now, pardon me. Just as in all of these problems, there is a trick that will make the math much easier. So I want to zoom in for a moment here on this internal algebraic expression. We can make 2/3 have a common denominator with 1/6, and then we can write this as a huge fraction with 6 in the denominator. And then we can use our trick to cancel the 6 here with that 6 in the denominator. But I'm going to have to show you how to do that over in side work. So let's get that side work going. The key is to recognize that you're always allowed to multiply by 1. Okay? This is a trick that will always help you. So 1 can come in many forms. 1 can be 1/1. 1 can be 2/2. And in this case, that's what we want. Okay? Let me show you exactly what I mean. If I take 2/3 and I multiply by 2/2, then what we're going to do is multiply across the top and across the bottom. And what I get is I get 4/6. So now this 2/3 is 4/6. Okay, so let me write out that step because I don't want to skip any intermediate steps and then lose people. So f of g of x equals 6, open parentheses, 1 over 6x minus 4 over 6, close parentheses, plus 4. And now you see, we have a 6 here and a 6 here. And when the thing separating those two denominators is an addition or a subtraction symbol, that means we can just put 1x minus 4 in the numerator and put a huge fraction bar and then just put a single 6 in the denominator. So let's do that. F of g of x equals 6, open parentheses, and we don't have to write 1x, but it's also not wrong, so we'll write 1x minus 4, big fraction bar, over 6, close parentheses, plus 4. And now you see, okay, this 6 is really 6 over 1, okay? So if I actually write it that way, didn't mean to do that. If I actually write 6 over 1 instead of 6, you can see what's going to happen. This numerator 6 is going to cancel with this denominator 6. And that gets rid of the parentheses. So now these parentheses go away, and so does this fraction bar. And all we're left with is 1x minus 4 plus 4. And that was the secret. So f of g of x equals, we can drop the 1, x minus 4 plus 4. Big brain time. Negative 4 plus 4 is 0. So we should do an intermediate step where I write f of g of x equals x plus 0, but we can also just do this so much faster. And I have this, f of g of x equals x. And that was one of the two things I had to prove in order to prove that these two functions are inverses of one another. So we did part A. Now part B is to just reverse that and do g of f of x. Part B. Okay. Part A is done. Let's do part B. So I need to see the original function. So this time I'm going to write g of f of x. And so the basic framework is going to be here. And this x is going to be replaced with f of x. And then in the second step, I'll replace the f of x with 6x plus 4. So 1 6x minus 2/3. Let me zoom back in here and say g of f of x equals 1 over 6, open parentheses, f of x. I just want to double check. I think it's minus 2/3, right? Yep. Minus 2/3. So now it's time to replace f of x with what f of x is equal to, namely 6x plus 4. So g of f of x is equal to 1 over 6, open parentheses, check it again to make sure, 6x plus 4, close parentheses, minus 2/3. Okay, now before you rush off and start distributing, just take a look at what you're about to do. You're going to distribute 1/6 to each term inside these parentheses. And as a result, you are going to have a denominator of 6 underneath 6x and underneath 4. Okay? So let's go ahead and do that. And then I want you to start looking ahead at this 2/3 and think about what we might be doing to that fraction here in a second. But let's proceed with the distributive property. G of f of x equals, so numerator times numerator, 6, and these parentheses disappear now, 6 over 6x plus 4 over 6 minus 2 over 3. Okay, so here we are. There's a couple ways we can do this. All right. First, 6 over 6 cancels down to 1 over 1, leaving behind just the x. Okay, so that's one thing. And now we have two choices. We can either convert 2/3 into a fraction with a denominator of 6 by multiplying 2/3 by 2 over 2, or we can reduce the fraction 4 over 6 by dividing the top and the bottom by 2. So if we divide 4 by 2, we get 2. If we divide 6 by 2, we get 3. So it's totally up to you what you do here, but I'll just show in side work. We'll do the fraction reduction method since we did the other way in the previous problem. So 4 over 6. If I divide the top by 2 and I divide the bottom by 2, I get 2 over 3. Okay, so now this 4 over 6 has become 2/3. Let's move on. You should see the exciting thing that's about to happen. G of f of x equals x, we got rid of all that with that reduction there, plus 2/3 minus 2/3. So the same thing minus itself is 0, right? So that cancels out. leaving behind just x. Very exciting. So g of f of x equals x. So big clap, because we proved the second thing that we had to prove in order to prove that f of x and g of x are inverses of one another. So our conclusion is as follows. What's listed first? F of x? Okay. So here's what we're going to write. F of x and g of x are inverses okay. Why? Because f of g of x equals g of f of x, because they both equal x, equals x. That's the proof, right? That's step 5 from the worksheet, the verification. So again, I think this conclusion is actually the more important part of the problem, is that you write that down and justify your conclusion or your answer, which in this case is just yes, right? I think I forgot to write yes in the previous problem, number 3. So let's go back to the actual worksheet. So now number 3 and number 4, we write yes and yes. Okay. Please do not turn in a document on Tuesday when you take your test. Don't turn in the document that says yes, no, yes, yes, right? That's not going to help you on the test. What's going to help you is to turn in that document with all of this work stapled to it, carefully labeled, so you can refer to it, so you remember how to prove that functions are inverses of one another. Now, this is exciting because we've reached a new section of the review. 5, 6, 7, and 8 just ask us to find the inverse of each function. Now, here's the problem with these directions. The process that you go through to find the inverse of a function is to change this function notation here to y, right? And then you swap the x and the y, and then you solve the equation for y. Here's the problem, and here's why I think these directions are incomplete. Because the thing that you find, like when you do that, is not necessarily an inverse function. And so IMHO, right, in my humble opinion, 5, 6, 7, and 8 cannot just be as simple as replacing this with a y and then swapping the x and the y and then solving for y and then just writing that down as an answer and just that's it, I'm done. Because you don't really know if the thing that you found is an inverse. It's not necessarily true that just swapping out the x and the y and then solving the resulting equation for y will result in a true inverse. The only way to verify it is to do this, what we did for 1 through 4. So it's actually 5, 6, 7, and 8 actually require all the work of 1, 2, 3, and 4, but they require the additional work of you deriving the second equation, or the second function, or proposed function, we should call it. Okay? Because we don't even really know if what you come up with is a function. So first it's got to be a function, and then you've got to verify that that function is in fact an inverse of the function that you started with. Okay? So just going to take a 2-minute break, and then we'll come back and start with 5, 6, 7, and 8. I'm really just creating this break to create a new section in the video. So I'll be right back. Okay, welcome back. So you see I've added some directions here. Find the inverse of each function and prove the two functions are really inverses. So we shouldn't do this, but we will assume. I won't tell you what assume means. Assume makes a something out of you and me. We shouldn't make assumptions, in other words. We should verify that these are all actually functions, because, they're given to us as functions, but they might not be functions. I can tell you that they're all functions just by looking at them, but you should verify that. Now, so the original rules were find the inverse of each function. But just going through that algorithmic process doesn't necessarily result in an inverse. So I added these directions and proved the two functions are really inverses. Okay, so you have to do that. Otherwise, you haven't really found an inverse. You've found a potential inverse, right? But you got to check it. I mean, look back up here. Look at number 2. I mean, that at first glance, you're not sure. Okay, so let's get into number 5, and I'm going to walk you through the full process. So I'm going over here with number 5. Okay, so in order to find the inverse of a function, the first thing you have to do is replace the g of x with a y. So let's just do it. So here's step 1. Okay. If g of x equals y, okay, we're assigning the letter y to the function g of x, then y equals negative 7x minus 5 over 8. Okay. Now in step 2, swap the x and y. That's all you got to do. So what we're going to do in number 2 here in part 2 is we're going to swap the x and the y. So we're going to put the x where the y is and the y where the x is. So now we're going to have x equal negative 7y minus 5 fraction bar over 8. Okay. So now in step 3, we're going to solve for y. Okay. So we need to rewrite this. X equals negative 7y minus 5 over 8. And this is where we get to do algebra. Yay! The class you signed up for, or were forced to do, one or the other. Okay, so before we just start doing algebra, let's think about what we're going to do. I see that in front of the y, there's a negative 7, and I don't like negatives in front of my y's. Okay, so ultimately, the sound you're hearing, this creaking sound, that's the table. Ultimately, when we get done with this, getting rid of the 8 in the denominator part, we want to quickly move that y to the left side of the equal sign. And we'll do that using the inverse operation of subtraction, which is addition. So we're going to multiply both sides by 8 and get rid of the 8 on the right. And then we'll have 8x equals negative 7y minus 5. And then we're going to add 7y to both sides. So we'll have 7y plus 8x equals negative 5. Okay? And don't worry, I'm going to walk you through the whole thing. So let's start by multiplying both sides of this equation by 8. So I'm going to multiply the entire left side of the equation by 8. And what I'm really doing is I'm multiplying it by 8 over 1. Right? So that way these numerators and denominators cancel. But what I do to the right side of the equation, I must also do to the left side of the equation to keep the equation in balance. Because algebra in Arabic literally means to keep in balance or to balance or something like that. Okay, so now that we've done that, we're going to eliminate these parentheses and get rid of all this red stuff and write down 8x equals negative 7y minus 5. And remember what I told you, we don't want that negative 7 in front of the y. So we can't just get rid of it, we have to add 7y to both sides. Kind of like that. And negative 7y plus 7y equals 0. Okay? But normally what I do and what a lot of teachers do is they just mark it out. So now we have 7y plus, because this is positive, 8x equals negative 5. We're not done yet because we want the y to be by itself. So right now, 8x is added to 7y. So before we can get rid of the 7, we have to get rid of the 8x. And we do that through the inverse operation of addition. So plus 8x, we're going to do minus 8x on both sides. Okay, again, 8x minus 8x is 0, but the shortcut is to just cancel it out, even though that's mathematically not proper, but it's a shortcut. So we have 7y equals, now proper notation is to put the thing with the letter up front. So I'm going to write negative 8x and then put that negative 5 here as a minus 5. And this is preparing us, we're setting up a slope-intercept form. That's why we put the x term first. Okay, so now 7 is stuck to the y using multiplication. So to get rid of the 7, we have to do the inverse operation of multiplication, which is division. And so what we're going to do is we're going to divide the left side by 7, but we're also going to divide the entire right side by 7 as well. And when I say the entire right side, I mean this whole thing here. Now, these 7s cancel out, leaving behind 1s, which we don't have to write. And we arrive at y equals. So this is a pivotal moment. But so far, we just have negative 8x minus 5 over 7. Now, I want to point out something. That is not only a valid answer, like that's a valid solution. So we want to say something here. And I'm going to write maybe, right? Because we haven't proven this. But maybe f inverse x, wait, was it g? It was, sorry, g inverse x equals, emphasis on maybe, g inverse x equals negative 8x minus 5 over 7. Now some of you are thinking, oh wait, shouldn't we make these fractions, like shouldn't we put the 7 underneath the negative 8x, and then the 7 underneath the negative 5. If you wanted to write this in true slope-intercept form, that's exactly what you would do. So you would write y equals negative 8 over 7x minus 5 over 7. So just a quick review, the slope-intercept form equation of a line is y equals mx plus b, where m is the slope. Remember, the slope is rise over run, and b is the y-intercept. So this right here is in slope-intercept form. All right. So, just like before, these are equivalent. So, these two equations are the same thing, just written different ways. So, again, maybe G inverse X equals negative 8 over 7x minus 5 over 7. Okay? So what we call these here are, you say something like possible conclusions or possible inverses, right? Possible or potential inverses of g of x. But we haven't proven that they are inverses. And that's the part where I added the extra instruction of you have to verify it. Okay? So we don't work with possibilities, we work with validation. So if you just write this down, if you just took one of these and wrote it down, I suppose according to the original instructions, it would be valid. But my additional instructions should have been there, in my humble opinion. So we're going to prove it. Now, there's a reason for everything that I do. I'm not wasting any of your time. So remember I said that both of these were identical? That means that both of these are also identical. And when we verify these possible inverses, one of these forms is going to be more useful or easier to work with in the verification process than the other. So let's go look at the original function g of x and see which one of these two equivalent functions would be easier to use when verifying. So look at g of x. Just look at how it's written. Okay? Negative 7x minus 5 over 8. Now you tell me. Look back here. Which one of the two, we'll call this one 1 and this one 2. Which one of these two looks easier to plug in right here? When we verify it. The one where we have multiple fractions or the one where we just have the one fraction? Okay, and in my humble opinion, this one is the easier one to plug in. Okay, so that's the one I'm going to use. Now, you can do whatever you want, right? But that's what I'm going to use. So let's move on to the verification process. Okay, so now what we're going to do is verify. We are going to verify if g of x and g inverse x, and here I'm going to put a little question mark, are true inverses. Now, this language or this symbolism here is going to get super confusing if I start nesting in g of g inverse x. You're going to get super confused. I would get super confused because here's what that would look like. G of g inverse x. That looks confusing to me. So the first thing that we can do in the verification process is we can assign f of x to our potential inverse g inverse x. So I'm just renaming, for the moment, g inverse x as f of x. Because if we look at step 5 from our verification, from our step in our worksheet, they're using f of x and g of x, so we should just keep that nomenclature or the naming conventions that way. So this is just temporarily. For the sole purpose of making it easier, okay? Okay, so we're going to assign f of x to g inverse x temporarily. And we agreed that we're going to use this version of g inverse x. So I want to just make this explicit. G inverse x equals negative 8x minus 5 over 7. Okay. What I'm going to do is I'm going to call this, for just temporarily, f of x. Okay. Again, just temporarily, to make things easier. So let's move on to the actual verification process. Remember, the verification process is what we're going to do is we will see if g of f of x equals x. Okay? Then we will see if the reverse is true. If f of g of x also equals x. Okay, that's the verification process. So let's get started with that right now. So first I got to remind myself what g of x was. Negative 7x minus 5 over 8. So what I'm going to do is replace this with f of x. Negative 7x minus 5 over 8. All right. Negative 7x minus 5 over 8. So what I'm going to do is I'm going to say g of f of x equals negative 7, open parentheses, f of x, close parentheses, minus 5 over 8. Okay, and what we're looking to see is, does this equal x? All right, so that's just, right, that's like what we're trying to figure out. So step 4 is to actually perform that substitution and put this in here. Okay, that's what we're going to do next. So g of f of x equals negative 7, open parentheses, big time, and we're going to write negative 8x minus 5 over 7. Now you see why I chose this version of the potential inverse. Minus 5 all over 8. Now it looks hard at first, right? But notice something. We got a 7 in the numerator and a 7 in the denominator. They cancel. Okay? But this is crucially important. That negative sign did not cancel. So what I'm left with here is a -1. Okay? And that's still got to be distributed. So don't forget that. So we're going to move on to step 5. G of f of x equals -1, open parentheses, -8x minus 5, close parentheses, minus 5, all over 8. Are you feeling like this is going to work out to be x? Because I'm having a good feeling about it. So remember, when you distribute -1, you're really just changing the signs inside the parentheses. So this is going to become positive 8x, and this is going to become positive 5. And the parentheses will all disappear. So here's step 6. G of f of x equals 8x plus 5 minus 5 over 8. Some wonderful things are starting to happen. What is plus 5 minus 5? 0. So we can cancel that out. This is so satisfying. I really hope that you find this to be cool. So G of f of x. I mean, we just proved that we did it right, you know? Or when we proved half. We have 8x over 8 and the 8's cancel. Leaving behind 1's, which we don't write. And so G of f of x equals x. That's important. We better put it in a red box. Now remember, that was part A of the verification process. Right here, this began part A. Yeah. And we succeeded. So we verified half, and now we just have to do part B. Remember, in part A we did g of f of x. Now we're going to do f of g of x. Okay. So what are we going to do here? We're going to see if f of g of x also equals x. And if that's true, then the inverse function that we found up here, the possible or potential inverses of g of x, we verify that they really are inverses. Okay. Now, just to review, we assigned this. Remember, we did this. We assigned this the label, the temporary label, f of x. Okay. We traded this complicated symbolism for this simple symbolism of f of x temporarily. So when I write f of g of x, I'm going to use this form, and then I'm going to put g of x inside there where that x is. That's where I'm going to stick g of x. Okay. So let's go back here. So let me just see if I'm going to get this in my head. F of x is negative 8x minus 5 over 7. Negative 8x minus 5 over 7. Negative 8x minus 5 over 7. So 2. F of g of x equals negative 8x minus 5 over 7. So we're going to write negative 8 open parentheses g of x close parentheses minus 5 the whole thing over 7. And now we're going to substitute in what g of x was right here in the parentheses. Okay, so we better go figure out the original g of x. Let's go back and look at the problem. Negative 7x minus 5 over 8. Negative 7x minus 5 over 8. Okay. So here in step 3, we're going to write f of g of x equals negative 8, big open parentheses, and I think it was negative 7x minus 5 over 8, but I just want to verify. Negative 7x minus 5 over 8. Okay. Just want to make sure. Negative 7x minus 5 over 8. Are you feeling good about this one? Are you starting to get the hang of it? Minus 5. And then this whole thing gets put over 7. You should feel pretty proud of yourself if you're keeping up with this. So to avoid confusion here, I want to just make sure that we remember that negative sign is going to stay there when we do this cancellation. So this 8 is going to cancel with this 8 right here. But that's going to leave behind a negative 1, all right, which we're then going to have to distribute. So just keep that in your head. So I'm going to cancel those 8s, but I didn't cancel the negative 1. You know, I can't reinforce this enough. Negative 8 is really equal to negative 1 times 8. So the thing that I canceled was the 8. and this negative 1 stays behind. It just wasn't written that way. You have to remember that. Okay, so we've eliminated the parentheses in the numerator. So in step 4, we're going to write f of g of x equals negative 1. And we always put that in parentheses so we don't forget that the negative and the 1 go together. And then we do open parentheses here, negative 7x minus 5. And before, when I said we eliminated the parentheses, what I meant to say was we eliminated the fraction in the numerator. We're about to eliminate the parentheses in the numerator. And this whole thing gets put over 7. Okay, now we're going to distribute negative 1, which just means that we're going to change these signs to positive. Okay, that's all it means. And we're going to get rid of the parentheses and simplify this thing way down. So here in step 5, we have f of g of x equals 7x plus 5 minus 5 all over 7. Now, 5 minus 5 is 0. It's tempting to rush to the answer, but we're going to do all the steps because we show all of our intermediate steps, every nitty-gritty detail. F of g of x equals 7x over 7. And those 7's cancel. Final step, f of g of x equals x. Amazing. So this is deserving of a red box, okay, because we just proved the second part of our validation. So part B is done. So look, we proved that g of f of x equals x, and we proved that f of g of x equals x. So now we can write our conclusion. And here I'm going to go back to I'm going to reassign. Well, okay. Here's our conclusion. G of f, well, sorry. G of x and f of x are inverses. Because g of f of x and f of g of x equal x. Now, we need to reassign f of x back to g inverse x. So this is where we get to say the cool symbol that I've been teaching you. Therefore, that's what this means. Therefore, since f of x equals g inverse of x equals, and then we had g inverse x was negative 8x minus 5 over 7. Since f of x equals g inverse x, which equals negative 8x minus 5 over 7, then g inverse x equals negative 8x minus 5 over 7. Is indeed the inverse function of, and what was our original function? G of x equals negative 7x minus 5 over 8. Period. Okay? So this whole thing is our conclusion. This is real math. Okay? Sticking all this in a calculator is not math, and just writing out that potential inverse without taking the time to go through the proof or the validation. Okay, this is what we want. Now we can state with assurance that this is our answer. Okay, so this is what you can go write in the answer field. Or you could write this one. Like if it was a multiple choice test, either one would be fine. But we proved that it's correct. So I'm going to go ahead and write just the negative 8x minus 5 over 7. So I'm going to write g inverse x equals negative 8x minus 5 over 7 as the answer to the to number 5. Negative 8x minus 5 over 7. Okay. And I'm making all these red so far. So I think I can make this red like that. Yeah. Okay. Cool. So we did number 5, and now we're going to do number 6. All right, students. So starting with number 6, I'm going to accelerate the process a little bit. I think we've got a good grasp of the basics here with inverses. We've only got 3 more to go. So I'm going to try to show you how quickly you can do these, because you're going to have to do them on a test. Obviously, you can't spend 3 or 4 hours working them out. So let me paste number 6 right here. Okay. So let's see if we can start a timer. All right. So when I hit start, I'm going to go through the process and try to explain it, but also try to go as fast as I think you can go. And we'll see how long it actually takes to do one of these problems all the way through. 3, 2, 1, start. Okay, so f of x equals 1/4 x minus 1/2. Step 1 in determining, we just assume it's a function, and determining the inverse is to rewrite this function using y equals. So y equals 1/4 x minus 1/2. And now we replace the x with the y. So x equals 1/4 y minus 1/2. And now we solve for y. Now because the coefficient for y is positive, we'll solve for y on the right, which means we just have to add 1/2 to both sides. And we'll have on the left side x plus 1/2 equals 1/4y. Now to isolate y, we'll multiply both sides of the equation by 4/1, which would be the reciprocal of the coefficient. And I am going to put 4/1 here instead of just 4, since one of our terms in this parenthetical expression here is a fraction. Now doing that allows us to cancel the 4's on the right, isolating the y variable. Now the reflective property of equality states that we can read this equation from right to left and left to right. It doesn't matter. So what we're going to do now is distribute the 4 into the parenthetical expression. So I'll have 4x plus 4/2. equals y. Well, 4x, and then 4 over 2 reduces down to 2, so it's 4x plus 2 equals y. Now, this is our proposed. Let me flip this now. We're assigning y the value f inverse x. Again, this is the proposed f inverse x, so what we're proposing is f inverse x equals 4x plus 2. And according to the problem, that's where you could stop. That was 3 minutes and 53 seconds, but we're going to keep going to check the answer. So to check the answer, we will assign g of x to f inverse x. So what we're about to do is test the validation by doing f of g of x and see if plugging this in here results in f of g of x evaluating to x. So the validation here, or the check, we're going to do f of g of x equals 1 over 4, and then instead of x we're going to write open parentheses g of x close parentheses minus 1/2, and then we're going to substitute in for g of x 4x plus 2, so we have 1 over 4 open parentheses 4x plus 2 close parentheses minus 1/2, and we should write f of g of x on every line. So it's a complete mathematical statement. And now we're going to distribute the 1/4 into both of our terms. So f of g of x equals 4 over 4x plus 2 over 4 minus 1 over 2. We notice that 2 over 4 can be reduced down to 1 over 2, so we see that those will cancel. And so we find that f of g of x equals, and of course 4 over 4 cancels down to 1 over 1, which just leaves behind x. So that validates the first test. Remember, this was part A. So here's part B, where we do g of f of x, and that is going to equal 4 open parentheses f of x close parentheses plus 2. And now I'm going to substitute in 1/4 x minus 1/2 for f of x. G of f of x equals 4 open parentheses 1/4 x minus 1/2 close parentheses plus 2. Now I'm going to distribute the 4 into the parentheses. So g of f of x, it will equal 4 over 4x minus 4 over 2x plus 2. And we see here that 4 over 2 is just 2. So we see we have minus 2 plus 2. That's 0. This cancels down to 1 over 1. So we have g of f of x equal to x. So we satisfied the validation, which states g of x and f of x are inverses because f of g of x equals g of f of x equals x. And now we can go back to what we found. Remember, g of x was equal to f inverse x, which was equal to 4x plus 2. And we can feel secure in putting a box around that and making that our answer. So what we're going to copy back to the page is f inverse x equals 4x plus 2. And stop. So explaining it took 10 minutes and 35 seconds. That's still too long, but that time I was explaining what I was doing. So this time, for number 7, I'm just going to run through it. Okay? So let me copy number 7 first. And then we'll restart that timer and see how fast we can go. Let me zoom in and prepare myself. And let's go back and reset the timer. And 3, 2, 1, start. Okay, so little error there on the computer. We're gonna start that over. Since that was a computer error, let me get back to where we should be. Somehow the paste got deleted. It's really weird. Okay. That won't happen on your test because you won't be using a computer. So let me go back and start this timer again. 3, 2, 1, start. Okay, so step 1. we replace f of x with y equals negative x plus 4. And then we swap x equals negative y plus 4. And now I'm going to add y to both sides to avoid the negative. And I'll have y plus x equals 4. Subtract x from both sides. Y equals negative x plus 4. So that would mean that if we stop there, f inverse x equals negative x plus 4, and stop time. So 1 minute and 12 seconds. Let's see how long it takes to validate that conclusion or that proposition by continuing the time. Okay, so if I want to validate this, first I'll assign it g of x. And then I'm going to do f of g of x equals negative, open parentheses, g of x, close parentheses, plus 4. Perform that substitution. F of g of x equals negative, open parentheses, negative x plus 4, close parentheses, plus 4. F of g of x equals, and now I distribute what is a negative 1. Remember, that just changes the signs. So now I have x minus 4 plus 4. Those cancel out. And that passes the first test because f of g of x equals x. So now we try g of f of x. And that would equal negative, open parentheses, negative x plus 4, close parentheses, plus 4. And I immediately notice something. They're identical. So in this case, the inverse of the function is identical to the original function. And you see here we're going to end up with the same, it's the same notations, the same structure. So we already know that this will evaluate, so it passes both tests. So we know that this is it. And we'll go back and write it. F inverse x equals negative x plus 4 for number 7. And stop time. Okay, 4 minutes. That's significantly better than 10 minutes or 30 minutes or 40 minutes or however long I've been taking to do these problems. So that's more in line with what you could do and still succeed on the test. So let's see if we can still keep our time around 4 minutes here with number 8. Let me grab number 8. Okay, for this problem, I noticed that when I opened that Edge browser to run the stopwatch, it was creating a memory issue with the computer. So you're going to have to trust me. I'm using my iPhone this time. So 3, 2, 1, start. Okay, so step 1 is to replace g of x with y equals -4 plus 3/5 x. And now switch the x and the y. X equals -4 plus 3/5 y. And we'll go ahead and solve for y on the right since it's positive, which means we just have to add 4 to both sides here. So on the left we'll have x plus 4 equals 3/5 y. And now I will multiply both sides by the multiplicative inverse of the coefficient of y, which is another way of saying the reciprocal. So I'm going to multiply both sides by 5/3. And that's going to cancel out everything here, leaving y by itself. So y will equal 5/3x plus 4/3. And since y is f, or in this case g inverse x, the time is now 1 minute 50 seconds. So we will continue. We will assign this the f of x to do the validation. So we could have stopped there at 1 minute 50. But what we're going to say here is that f of x, which we know is the inverse that we found, is equal to 5/3x plus 4/3. Another way to write that is 5x plus 4/3. Since they have a common denominator, I can do that. And so now what I'm going to do is g of f of x, which will equal -4 plus 3/5, open parentheses, 5x plus 4, fraction bar 3, close parentheses, and I see that I can cancel the 3's here. And so now I've got g of f of x equal to -4 plus, and what I'm going to distribute, well, I'll go ahead and write this intermediate step. I've got 1/5, open parentheses, 5x plus 4, and I'm going to go ahead and put over 1, just so there's no confusion about what I'm about to do. I'm now going to distribute 1/5 to both terms. So g of f of x equals -4 plus 5/5 x plus 4/5. And we have a problem because I don't see how this is going to resolve into just x by itself. Let's make sure that we found our inverse correctly. I added, and then I multiplied. By the inverse. Okay. I don't know, guys, because now g of f of x equals -4 plus x plus 4 over 5. Now that does not equal x. That's a problem. Let's try it the other way around. Let's try f of g of x There could be a clerical error somewhere in here. I'll check it if this doesn't work. So f of g of x equals 5, open parentheses, g of x plus 4 over 3 and then I'll substitute in what g of x is. So f of g of x equals 5, open parentheses, and then g of x we found was given to us. So g of x is -4 plus 3/5 x. Close parentheses, plus 4 over 3. So now I'm going to distribute multiply 5 over 1 to both terms here. And that is going to give me negative, so f of g of x equals -20 plus 15 over 5, x plus 4 all over 3. So f of g of x equals negative 20. 15 over 5 reduces down to 3 plus 3x plus 4. So I can do negative 20 plus 4, which would be negative 16, and I end up with f of g of x equal to 3x minus 16, which is not equal to x. So one of two things have happened here. Either there is no inverse, or we did something wrong. So before we assume that we did something wrong, we just start over, okay? So this is going to be our second attempt at number 8. I'm going to call this the second attempt. And let's see if we can do this, and we see if we get a different result. So the first thing I'm going to do is replace g of x with y equals negative 4 plus 3 over 5 x. And just to try something different, I'm going to write negative 4 with the denominator of 5 by multiplying negative 4 over 1 by 5 over 5, which will give me negative 20 over 5. And that allows me to write y equals negative 20 plus 3x all over 5. And now I'm going to switch the x and the y. So x equals negative 20 plus 3y over 5. So the reason I'm switching up my methodology is because something went wrong, right? And what I'm going to do now is multiply everything by 5 over 1, or just by 5. So now I have 5x equals negative 20 plus 3y, and I'm going to add 20 to both sides. So I'll have 5x plus 20 equals 3y. And then I'm just going to divide everything by 3. So on the right hand side, I have y, which would be my inverse, equal to 5/3 x plus 20/3. Which we are calling G inverse x. Now let's see how that compares to what we did before. Yeah, now here I got 5/3 x plus 4/3. And over here I've got 5/3 x plus 20/3, which is different. So let me try to test this. Okay, so let's assign G inverse x the value or the function name f of x, since the other one is g of x. And what we're going to do now is that validation test. G of f of x equals -4 plus 3/5 open parentheses f of x. Remember, f of x is what we think the inverse is. Okay, so just like before, 5/3 x plus 20/3 can be written as 5x plus 20/3. So g of f of x equals -4 plus 3/5 open parentheses, and now I'm going to write 5x plus 20 all over 3. And then close those parentheses. And I'll cancel the 3's here. Remember, those leave behind 1's, not 0's. So now g of f of x equals -4 plus 1/5 open parentheses. This is going to work out. 5x plus 4. It's weird. I'll have to see what I did wrong in that other problem, because this is going to work out. G of f of x equals -4 plus, when I distribute the 1/5 here and here, no, it's not going to work. So it's going to give me 5/5 x plus 4/5. So that cancels down to be 1/1. So now g of f of x equals -4 plus x plus 4/5. Oh wait, I see my error. I wrote 4 right here instead of 20. Okay. Why did I write 4 right there? I don't know why I did that. It's very strange. But that distribution will give us 20 over 5, which reduces down, if we divide both top and bottom by 5, as 4 over 1, also known as 4. So now I get to cancel the 4's, leaving behind x. So g of f of x equals x, which passes the first test. And we just need to see if we can pass the second test now, which is f of g of x, which equals, we said f of x was equal to 5/3 x plus 20/3, which we wrote as 5x plus 20 over 3. So that's going to be 5, open parentheses, g of x plus 20 over 3. And g of x is negative 4 plus 3/5 x. So f of g of x equals 5, big parentheses, and that's negative 4 plus 3/5 x. Plus 20 all over 3. Now this is 5 over 1. So f of g of x equals negative 20 plus 15/5 x plus 20 all over 3. So f of g of x equals, those cancel to 0 because negative 20 plus 20 is 0. And then 15/5 cancels down to 3. So now I've got 3/3 x, which cancels down to 1 over 1. And so that passes the second test, confirming that there really was a valid inverse, and it was this 5/3 x plus 20/3. Okay, so we can say that g inverse x equals 5/3 x plus 20/3, or you could write it g inverse x equals 5x plus 20 over 3. And that would be valid the time kind of got away there. Let's see how much time we spent on this. 24 minutes and 49 seconds. Now my question is, what happened here on the first attempt? I'd like to know what I did wrong. So oh, I see what I did wrong. Now I see what I did wrong. I wrote 4 over 3. When I distributed this 5/3, I should have gotten 5/3 x plus 20/3, which is what we got. Okay, that was a really silly mistake, which is what we got over here. Okay, so I don't remember when we got that. It was like 1 minute and 50 seconds. I just failed to distribute the 5 properly. You see? Look at, I made a stupid mistake right here. I distributed the 5/3 here, and then for some weird reason, I didn't multiply 5 times 4. I just wrote 4 over 3. So I'm sure a lot of you caught that when I did it, but mistakes happen. And actually, if anything, that highlights the benefit of the validation testing. It also highlights the benefit of never giving up. So we tried it again and we got it right. Okay, so let's copy that over. 5x plus 20 over 3, or 5/3 x plus 20/3. And since I'm assuming that we're moving towards a graphing, we're going to write it in slope-intercept form. So g inverse x equals 5/3 x plus 20/3. And we did validate that. Okay, that was actually the last inverse problem. The rest of the test is significantly, well, I don't want to say significantly easier. 9 and 10 could give us some problems, especially number 9 could give us some problems. But the inverse problems are done. So we'll take a break, and when we come back, we'll start with 9, 10, 11, and 12. And then 13 and 14 are weird, like you have to write it out. And then we evaluate for 15 and 16. That's super easy. You're just plugging in the numbers. Then we're going to run the vertical line test here and find out that 19 and 20 aren't functions, and then state the domain and range. So these aren't functions at all, so we don't have to do that. They're, well, I don't know. Maybe we have to write the domain and range even if they're not a function. Not sure about that, but for 17 and 18, the domain and range for number 17 are all real numbers, and they want us to use set builder notation. So I'll show you what that is. That's different than the inequality notation that you used on the star test in Algebra 1. But that's going to be all real numbers, negative infinity to positive infinity. And here the domain will be negative infinity to positive infinity, but the range will be -4 to positive infinity. Again, I don't know if they want us to state the domain and range of 19 and 20 since they aren't functions, but we will, just in case. And then I guess we continue the process for 21 through 24. Number 21 is a function. Y equals 2 is a function, so flat lines are functions. This is not a function, right? The x's repeat. It's not a function. But we could theoretically state the domain and range as a discrete set. I don't know if, I guess they want us to do it even if it's not a function. That's what I'm gathering. And then numbers 25 and 26, it's going to be just like numbers 15 and 16, only they're giving us three different numbers to plug in instead of two different numbers. Is that what I'm gathering? Yeah. And then we'll be done. So when we return from our break, we're going to do composition of functions, and then we're going to add functions and evaluate, and then subtract functions and then evaluate. So we will be right back. All right, students, so here we are on number 9. This is called composition of functions. That little open circle is not a multiplication symbol. So let's go ahead and grab number 9. I'll show you what to do. And guess what? You've been doing it all along. So this is going to be review, since we've literally been doing this the whole time. All right, where am I going to post this? I think I'll post it here. So, as I said, you've done this already. So the question's asking you to compose the function g with the function h. And all that really means is what you've already been doing, which is to say g composition h of x is equal to g of h of x. See, you've already been doing that, right? So this is equal to 4 open parentheses x cubed minus 1 close parentheses plus 5. So the composition of the functions g and h of x is equal to 4 open parentheses x cubed minus 1 plus 5. So let's keep it rolling along. The composition of functions g and h of x is equal to, and now we're going to distribute 4. So we have 4x cubed minus 4 plus 5. And there's just one more step. the composition of functions g and h of x is equal to 4x cubed plus 1. And you are done with number 9. So function composition is something that you've been doing every single time you've validated your inverse function. It's the same thing. It's just a different notation. So let's go back. So 4x cubed plus 1. So what we're going to write down as our answer is the composition of functions g and h of x is equal to 4x cubed plus 1. Moving on to number 10, it's another composition of functions, and this is the composition of f and g. So at this point, if you've been validating all of your inverse function problems, you've done this 8 times on this paper already. So we'll put number 10 right here. Now let's move that and resize it so it's about the same size as the other one. Okay. So composition of functions f and g of x is equal, or I should say equivalent to, f of g of x, okay, which is what you know how to do already, which is equal to 3 open parentheses 3x plus 2 close parentheses. So the composition of function f and g of x equals 3 open parentheses 3x plus 2, and then we do the distributive property. And we find that the composition of functions f and g of x is equal to 9x plus 6. So the composition of functions f and g of x equals 9x plus 6. And that is the answer. Not hard at all, right? So 9x plus 6. So the composition of functions f and g of x is equal to 9x plus 6. Now, in the next 2 problems, we are asked to add the functions together. Well, in the next problem, we're asked to add the functions together and then evaluate the sum of those two functions at -1. And then in number 12, we were going to subtract function f from function g, and then we take the difference of those two functions and we evaluate that difference at -9. So let's clip out number 11. And find a place to put it. Put it right here. So I have a way of adding functions together that might be a little bit different than the way that you have been taught thus far. I use a method where we stack the functions. So certainly, if the way that you've been taught to do g of x plus f of x, where g of x equals -3x squared plus 2, and f of x equals x minus 3. If the way that you've been taught to do this thus far is to simply write down -3x squared plus 2 plus x minus 3, and then combine like terms, you would get -3x squared plus x minus 1. And the only two terms that you would combine are +2 and -3. Now, what they want us to do is evaluate that, right? So this is g plus f of x. But now they want us to do g plus f of -1. So what we would do is simply substitute in everywhere we see an x, a -1. Okay, the order of operations becomes extremely important here. So g plus f of -1 would equal -3, and then you do this first. You square -1. Now, squaring a negative number makes it positive, and 1 times 1 is 1. So this is -3 times 1. And then plus -1 just means -1, and then -1. Now, these two things together is like saying -1 plus -1, which would equal -2. So g plus f of -1 would equal -3 times 1 is just -3 minus 2. So g plus f of -1 would equal -5. So if that's how you've been taught to do these problems, it works when the problems, it works pretty easily when the problems are really simple. Okay, when the given functions are straightforward, especially when you're only being asked to evaluate an integer value, okay, like a whole number or a negative number where it's just a number, it's not a fraction, or it's not an algebraic expression. This can get way more complicated. So I suppose in this particular case, it's not really important whether you use the stacking method or the method where you just write it all out. But I want to show the stacking method because as these problems get more complicated, the stacking method is one way of making sure you make no mistakes. So we'll call this method 1. Okay. And then this is, my method is called the stacking method. Let's see if we get the same thing, and let's see what you think of it. Okay. So the stacking method. What it has you do is it has you create columns based on the exponents. Okay, so here the exponent is 1. That's important. So each exponent gets its own column. So in the stacking method, we're going to add g plus f, right? In the stacking method, we would write negative 3x squared. And then notice that we don't have anything in g of x where it's just x by itself. We just jump right to the whole number. So what we would do is we would put in plus 0x. Okay, because that's 0x to the first. And then we'll put plus 2. Now beneath that, we have x to the first minus 3. So remember, we put the exponents and group them together in columns. Okay, so here we would put 1x to the first, and then we would put plus negative 3. And now, like I said, this particular problem, it doesn't really matter. And unfortunately, you're not given any problems in this problem set where it does matter. But I'll just show you the method. So we create these columns, and you just add the columns. So like here we have 0x squared. So we just add column by column. Negative 3x squared plus 0x squared is negative 3x squared. 0x to the first plus 1x to the first is just plus x. 2 plus negative 3 gives us negative 1. And so you see we've arrived at the same sum as we did here. And then you would just evaluate that at -1. So you would say g plus f of -1 equals, well, I don't want to get rid of the columns because I want you to see them in your notes. I'll just write this lower. G plus f of -1 equals -3, open parentheses, -1 squared plus, open parentheses, -1, close parentheses, -1. So again, g plus f of -1 would equal -3, and then -1 squared is 1. And then we just have -1 -1. So g plus f of -1 equals -3 minus 2. So g plus f of -1 equals -5. And again, you're going to get the same answer both ways. What I'm trying to warn you about is down the road, when you're evaluating something much harder than just a number, and when your original given functions are way more complicated than this, the stacking method can save you, especially when they're all mixed up, like they're not in order. You have to reorder them. You could even be given like 5 functions and asked to add all of them together, and it just, if you were to try to write it out in one big line, it would become a complete nightmare of trying to find the like terms. And so the stacking method's benefit is that it does the like terms part automatically. Okay, that's the benefit of the stacking method. So personally, I recommend the stacking method. Here's one thing that I absolutely do not recommend that you do. Notice that in both of these methods, first thing I did was I added the two functions together as functions of x. And then only when I had the sum of those two functions did I actually evaluate at the number that they wanted us to evaluate. What I see in a lot of the homework problems and the tests that I'm grading, even in pre-AP, is I'm seeing students attempt to jump and plug the -1 in the very first step. And that is, there are so many chances for errors when you try to do multiple steps at once. It's also not mathematically accurate to do it that way. The problem is asking you to do a certain thing in a certain order. The sequence is add g and f and then evaluate that sum at -1. It doesn't say plug in -1 everywhere you see an x and then add it all up. That's a recipe for disaster. Okay? It's a shortcut, but it's going to get you in trouble. So Anyway, in this case, g plus f of -1 equals -5. I'm just warning you. So we write g functions g and f, the sum of functions g and f evaluated at -1. See, when I say it that way, it actually tells you what to do. The sum of g and f, okay, evaluated at -1. So there's a step in there where it wants to see the sum of g and f. If you're just plugging this number directly into the functions and then adding it up, you're not actually finding the sum of the functions. You're just plugging numbers in, okay? So anyway, let's move on. I wish they'd given you in this test review a harder thing to evaluate, so it would just very clearly demonstrate what is wrong with the method of just trying to plug it in real quick and rush through the problem. So let's do number 12. This is a subtraction, and subtraction, in my opinion, makes the stacking method even more crucial, because otherwise you're going to have to distribute a negative. So let's go here, and this is number 12, and we'll put number 12 right here. So here we're asked to subtract f from g first, okay? So basically you need to ignore that -9 and just do this for x first, okay? And then do it for -9. All right? That's how I'm going to teach it, and that's how I want you to do it, so that I can see that intermediate difference as a function of x. Okay, so I'm going to use, again, both methods, since some of you have only been exposed to the method that I said I don't like. So here's that method. I guess I'm going to call it the line method. Maybe this will demonstrate to you something. So what you're going to do is you're going to take g of t and subtract f of t. Okay, so what does that look like? Well, g of t is 4t plus 4. And then you're going to subtract t plus 1. Now, if you write it like this, you're going to get it wrong. Okay, because you must distribute that negative symbol. So even if you're going to use the line method, a much better way to write it would be g minus f of t. Okay, I wrote x over here, I meant t, equals 4t plus 4 plus, and then you go off to the side, you're going to write -1, okay, in parentheses, and then you're going to do an open parentheses and write t plus 1. And then you're going to close those parentheses off. And that is going to tell you what you need to do, right? You got to distribute that -1. Otherwise, this whole thing falls apart. So what would that equal? 4t plus, except we're going to have t's and pluses that look the same, 4t plus 4. And then let's see what happens. We get -1 times t is minus, and then I recommend writing 1t. All right, so you know what the coefficient is. That's another landmine. -1 times 1 is just -1, which I would prefer that you write plus -1, like that. There's a reason for it. So now you're going to combine like terms. So here are the linear terms that are like, and here are the constant terms that are like. Okay. So that was g minus f of t. Notice I still haven't messed with this -9 at all. So let's now combine the like terms. We have g minus f of t equals, now let's do the pinks, 4t minus 1t is 3t. And then 4 plus -1 is 4 minus 1, and that's minus 3. Okay? Now, I see something that we can do, and you can only see this if you first find the difference of the two functions of t and not of the number. Okay? I see something that we can factor out. And again, right now, it's not absolutely crucial that you do this, but the greatest common factor of those two terms is 3. And so you can actually pull that 3 out like this. You're basically dividing it out. Let me show you what that looks like. So now function g minus function f evaluated at t is now equal to 3 open parentheses t minus 1. Okay? This isn't important right now, but it will be important later that you know how to factor out the greatest common factor. So this would be a step that I would like to see, regardless of whether you use the line method or the stacking method. So now we're going to evaluate this at -9. So we have g minus f, or the difference of functions g and f, evaluated at -9 equals 3 open parentheses, and then we're going to do open parentheses -9 where we see the t, close parentheses, minus 1, close parentheses. Okay? So the question is, we do what's inside the parentheses first. What is -9 minus 1? -9 plus -1 is equal to -9 minus 1, which is equal to -10. So I like to think of the minus, I like to think that there is no such thing as subtraction. There's only the addition of negative numbers. I read that in an advanced math book one time. So we have the difference of functions g and f evaluated at -9 equal to 3 times -10. So the difference of functions g and f evaluated at -9 is equal to -30. Okay. That is the line method of doing this. So what would the stacking method look like? Again, don't judge the method by this problem, because this is too simple for the method that I'm proposing to show its true benefits to you. But here's the stacking method. Now I'm telling you, there's going to come a time in this class when the only way to do it is to stack it, or the only way to do it with any reasonable chance of getting it right is to stack it. So we don't have any quadratic terms. That would mean t's raised to the power of 2. We just have the linear terms where the exponent is 1. And remember, in front of that t there's a 1. So what we would write is we're subtracting f from g, so we put g on top. 4t plus 4, and then underneath it we would write 1t plus 1, and we put that in parentheses because we're subtracting, and we put a big minus sign out here. And we take our ruler, draw a line, then we make our columns. Okay. Now, in this case, there's only one column, right? And it doesn't even need to be that long. It just needs to be like this. So here's how you do this. I'm going to use a different pen. You say with your finger, 4t minus 1t. 4t minus 1t is 3t. All right, so let me get rid of all those dots. So the dots represent you with your finger on the paper, right? So 4t minus 1t equals 3t. And now you come over here. And again, this dot is your finger. 4 minus 1, right? So your finger is moving to the minus symbol, and that's essentially performing the distributive property. You're just saying it in your head. 4 minus 1 is 3. Okay? So, positive 3. Let me get rid of the dots. So we put plus 3. So let's see what we have here. The difference of functions g and f with respect to t, okay, or evaluated at t, is equal to 3t plus 3. Okay, I just noticed a mistake in my own work. Over here when I was combining like terms, 4 plus negative 1 isn't negative 3, it's positive 3. So this would be t plus 1. So when we evaluated it, it was going to be negative 9 plus 1, not negative 9 minus 1. So this is negative 9 plus 1 equals negative 8. Well, I don't want to delete. I want to show the wrong work and then scratch it out, okay? So this should have been minus 8, which means this should have been negative 24. All right, let's see if we get the same answer here. That kind of just proved my own point, I think, there. The reading left to right method and combining like terms is prone to error, where the stacking method is much less prone to error. So there's a perfect demonstration. All right. So now we can go ahead and evaluate this at negative 9. But before we do that, let's do the thing that I noticed before, which is that we have a greatest common factor that we can factor out. In this problem, that greatest common factor is 3. So that can come out here. I'm telling you, later on, factoring out the greatest common factor will make your life infinitely simpler. Even though in this particular problem, it's kind of irrelevant. G minus f of t equals 3, open parentheses, t plus 1. Okay, you see how the thing inside is now simpler? You've also factored this, which becomes important later on in Algebra 2. Factoring by grouping requires you to factor out the greatest common factor twice. So honing that skill now will help you later on. So now let's do the difference of function g and function f evaluated at negative 9, which would be equal to 3, open parentheses, and then open parentheses, negative 9, close parentheses, plus 1. So the difference of functions g and f evaluated at -9 equals 3, open parentheses, -9 plus 1 is -8. So the difference of g and f, functions g and f evaluated at -9, is equal to -24. In my opinion, it is utterly crucial that you get to this point here. And there's a reason for that. And I'll tell you the reason right now. I'm going to make the point. Why is it important that you arrive at the function, the difference with t, with respect to t, and not just jump right in and plug in the number? Okay, here's why. Let me open up a browser window and go to Desmos. I'm going to prove a point to you. No pun intended. I'm literally going to prove a point to you. So, -9 is the input value. That's always thought of as kind of like the x value or the independent value or the domain value. Okay, input x, independent, domain. Okay, these are all words that describe -9. In this case, they were using the letter T. Okay, whatever. All right, the thing inside the parentheses that you're evaluating the function at is the input, the independent variable or number, the x or whatever letter they're using, or the domain value. Okay, this is the value along the horizontal axis. Okay, now in a similar fashion, let's use blue. -24 is the output value. That's what we typically call y or f of x. Okay, or in this case, we're calling it the difference of g and f. Okay, this is the dependent number. In other words, this number depends on what you plug in. It changes depending on what you plug in. And this is what's going to be plotted as the range value. And this is going to be on the vertical axis. Okay, so all of these things describe -24. The thing I want you to pay attention to is this is x and this is y. So if you put them together with a comma in between them, you have a coordinate pair. So if I rewrite g minus f of t as y, then I have back to my original equation, this is why it's so important. I have y equals, remember this, all of this gets replaced with just y. Y equals 3, open parentheses, and then to turn this into an equation that we can graph in Desmos, we're going to replace that t with an x. So y equals 3, open parentheses, x plus 1, close parentheses. Y equals 3, open parentheses, x plus 1, close parentheses. Well, now, if you wanted to write this in slope-intercept form, it becomes obvious. You would just redistribute the 3, and you'd have in slope-intercept form y equals mx plus b, where m is the slope and b is the y-intercept. You would have y equals 3x plus 3, which tells you that the slope is 3. So that's a rise of 3 and a run to the right of 1. And this over here is the y-intercept, right? That's the y-intercept. And this tells you that the line crosses the y-axis at 0, 3. Okay, so here's your slope and here's your y-intercept. And if you had to, you could go and create a graph, which I'll do right now, and sketch this function with no trouble whatsoever. Okay, let me show you how easy it is to sketch this function now that you have this information. So I'm going to delineate here 1, 2, 3, 4, 5, 6, and I'm going to call this y and this x. Remember? And then using the same spacing 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It's not perfect. Doesn't matter. 2, 3, 4, 5, 6. Okay, so what I'm going to do first is plot my y-intercept. And that would be located at 1. So this is the origin point, 0, 0. This is 0, 1, 0, 2, 0, 3. There's my y-intercept right there. Okay. So I want to make this note. Right there is my y-intercept. And that's located at 0, 3. Now from that point, I can plot the entire line. All I have to do is use the rise and the run. So I'm going to rise up 3, and then I'm going to run to the right 1 space, and I'll place my next dot. So look, you rise up 1, 2, 3, and then you run 1 to the right. So over 1. Right there is another point on the line, and you only need 2 points to plot a line. But we could do it again in reverse. So instead of doing a rise of 3 and a run to the right of 1, we could do a fall of 3 and a run to the left of 1. Okay, so now we have 3 points plotted, and if you have a straight edge, it's very easy to draw or sketch quickly the graph of the line. Let me find a color we haven't used yet. Blue. So there's your line right there. That's what it would look like. And the equation of that line is y equals x plus 3. But this is also, y equals 3x plus 3. But we can now substitute back in g minus f of t in function notation. We could say g minus f of t equals 3t plus 3. And this line is also described, okay, by that function. So here's the point I'm getting at here, and this is why I want to use Desmos. Functions can be written as lines, as the equation of a line. It is really important that you understand these things, okay, about the input and the output, so you understand what you're doing. When you input -9 and you evaluate the difference of g and f, you get -24. So what that means is that somewhere on that graph that we just drew, which we're not going to draw out to be big enough to see these points, but here is what I'm trying to tell you. Somewhere on this line, okay, somewhere on that line, this is the one I'm going to plot in Desmos. Somewhere on that line is the point -9, comma, -24. Guaranteed. And if it's not on the line, then we did something wrong. Okay? So let's go check. We'll write y equals 3x plus 3. And then we'll put in the coordinates -9, comma, -24. Okay? And I'll label that the point. Okay? Let's zoom out and see. Look at that. There it is. So it's on the line, isn't it? And that's the point I was trying to make to you. Now look at the line. Doesn't the line look just like the thing we sketched? We determined it looked pretty darn close, like it crossed the x-axis at -1, comma 0. The x-intercept being -1, comma 0. Let's see if we were right. Wow. So you didn't need a calculator or a computer. You could just draw it. Okay? And now we know a lot more about this topic than we used to. Okay? And I want to make this point. This is the input of -9 and the output of -24. Okay? So I'm going to save this graph. What number is this? Number 12. I'm going to save this graph as number 12 from test review 1-1 Alg 2 academic Morelli, and then today's date 09/04/2021. Let me save that and let me share it and paste it into the OneNote so that you have access to this. Is it frozen? Okay, there we go. What's going on? It's like it's frozen. Hang on a second. Okay. Yeah, it was kind of frozen up there for a second. So now, if you were to load this up in your class notebook, you would actually have a working version of Desmos right here inside your class notebook that shows that point plotted on the line so that you remember the relationship that I'm talking about here. Okay, so let's get back to just answering the question. So the difference of G and F evaluated at -9 is -24. Just hoping I can get this written down, and then I will give the computer a break. I can tell it's overworked. Let me close this browser. That should help. Okay, I think I'll be able to get this written down, and then we'll have to take a break and let the computer cool down. So the answer to the question is the difference of functions G and F evaluated at -9 is -24. Okay, so that's what you would write, but you saw all the work that we did on this side. So we'll take a break and let the computer cool down because I can feel the heat on the touchscreen. When I use the pen on the touchscreen a lot, and especially when I've got multiple applications running and I'm recording, it's just maxing out the CPU and it's throttling down and it freezes the computer. So let's give the computer a break, and when we come back, it'll be cooled off and we can continue. All right, well, let's continue on to number 13. So, when is a relation a function? What are some ways to tell if a relation is a function? Well, the main thing that you want to know here is that the x slash domain slash input slash independent variables do not repeat. So the x's cannot repeat. That's one way to tell that a relation is a function. It's okay if the y slash range slash output slash dependent variables repeat, but it's not okay if the x domain input independent variables repeat. Okay? What is the domain of a function? What is the range of a function? So now we're looking at number 14. Given a member of the domain, how do you find its value in the range? Okay, well, there's 1, 2, 3 different questions here, and there's no space to write sufficient answers to these questions. So I'm going to write up here number 14. I guess we'll say, question 1, right? What is the domain of a function? Okay, I would say this. The domain of the function How do you phrase this? The domain of a function is a because I want to use the word range here, but it is a I don't want to say list. Here's what we could do. We could write the domain represents the set or interval of all possible x slash input slash independent values for which the function is defined. It took me a minute to try to come up with a good answer for that, because that's a big question, because the domain could be all real numbers, okay? But the domain could also be just a list of numbers. For example, if the function was what we call a discrete function, maybe the domain is just 1, 7, and 350, right? In many cases, especially when there's a continuous line that doesn't have any vertical parts to it and has no gaps with open circles, we'll call that like a continuous function. Then the domain would be all real numbers, or negative infinity to positive infinity. And what numbers are we referring to? We're referring to the numbers that would go in here, okay? What you would put into the function. That's why I'm calling it the input, the x, right? And then these values are called the independent values, or the independent variables. Okay, so when we're talking about domain, what we're talking about are all of the values for which the function is defined by its input. The range is exactly the same sentence, sort of, right? What is the range of a function? The range of a function, and we'll try to verbally talk about this before we put something down in print, right? Because we don't want to say something juvenile, right? We don't want to just say, oh, it's all the y values. We want to say something more abstract, something more high level, something more mathematical, right? More rigorous and more broadly defined, right? Because it's not always y. So we want to say something like, the range represents every single output which is defined by any given input. So, just as an example, as we're forming up our answer here, if I have f of x, okay, this, whatever this is, right, whatever this equals, is going to be a range value. Right, that's the output. So the x is the input, and once you evaluate the function at that input, the result of that evaluation is the range that corresponds to that domain value. So I want to say something that sticks with this kind of language, okay? So it's just not as simple as it looks to just say it. You want to say something simple like, oh, it's all the y values, or it's all the vertical, it's on the vertical axis, something like that. But that's not really what, because we're not always talking about graphs. So what we're really talking about is the range represents every output value which is defined by every corresponding input value. Let's see if that meets all of our needs here. The range represents every output value which is defined by every corresponding input value. Yeah, I mean, I think that could be refined in certain ways, but that's probably good enough, okay? Because we want to use function language here. Right? We don't just want to say every y that corresponds to every x, because it's not always x and y. We want to think of x as an input value, and we want to think of y or f of x as the output value. All right, you think of a function like a little machine. You put something in, and then whatever it spits out, that's a range value. The thing you're putting in is a domain value. Okay? But we had another phrase here. We were talking about independent variables. So we also want to mention instead of saying the range represents every output value which is defined by every corresponding input value, we might just want to write above output value. The range represents every dependent value, for lack of a better word, which is defined by every corresponding independent value. Okay, now we will definitely want to include this notation, something like every f of x given by all x values for which the function is defined. Now that's too specific because it could be g of x or p of r, right? But if we're using f of x, we say every f of x given by all x values for which the function is defined. I think that explains what the range is. I think these two sentences, actually these are three sentences, right? Because we've got sentence number one reads, the range represents every output value which is defined by every corresponding input value. That's the A way of reading the sentence. The B way of reading the sentence would be, the range represents every dependent value which is defined by every corresponding independent value. And then we have this more practical definition. The range represents, okay, every f of x given by all x values for which the function is defined. All right, so now what was the third question? Given a member of the domain, how do you find its value in the range? All right, this is more straightforward. Sort of, right? So let's write small. You find no, we need to start this. This is question 3. Okay, we need to think about this. Given a member of the domain, how do you find its value in the range? All right, so what you're looking for here is, given any domain value for which the function is defined, you find its corresponding range value by evaluating in other words, plugging in, evaluating the function at a given member of the domain. Let's see if that makes sense. Given any domain value for which the function is defined, you find its corresponding range value by evaluating the function at a given member of the domain. Okay, we want to say a little bit more here. We want to say something like, the result or output of such an evaluated member of the domain is by definition its corresponding value, well, corresponding range value. I know it looks like we wrote an essay here, but it's not, these are difficult questions. Like, there's no simple answers here, okay? We have to think carefully about what do they mean by domain. It's not just all the x values, right? It's all the x values that will produce, that the function will evaluate to a defined point on, right? So if you stick in an x value and the result is not defined, then that wasn't a member of the domain. Okay, so then there wouldn't be a corresponding range value, right? See, first you have to have the domain be the set of all numbers for which the function is defined. Okay, and there can be an interval, right? And that interval can be infinite. It can be a negative infinity to positive infinity. The range is the mapped, it is the output value to which the input value maps. That's another way of saying what the range is. You've seen those circles before, right? Those we call like maps, where you've got x and then f of x, and then there's like numbers 2, 3, 4, 5, whatever, and then 15, 19, 32, okay, and then there's like lines. Now it's okay if multiple domain values map onto the same range value. That's fine. Okay, so that's why I drew it that way. But it's not okay if more than one line comes out of one of these numbers over here. So that's what's meant by mapping. In practice, it's just you stick in an x value and you go ahead and crunch the numbers of the algebraic expression, and then you should get you might get another algebraic expression as a result, but that would be the range, right? The output of the input. So I hope that we've elucidated enough for this review anyway. Number 14's very complicated questions. And then, for number 13, we kind of failed here. When is a relation a function? What are some ways, okay, to tell if a relation is a function? And all we did was list one thing. The x domain input independent value doesn't repeat. And so I think there's more that we could say about that, but that's all that's coming to mind right now. So let's move on to this next section here. because this is just a big minefield, right? You could spend days talking about this. This is a very philosophical issue. So this is number 14. All right. All this goes with number 14. Okay, well anyway, let's move on to number 15. So number 15. If f of x equals negative 4x minus 7, find f of 3 and f of negative 7. So this is a domain value. This is a domain value. And when you stick these numbers in here, okay, which means putting them where that x is, and then you crunch the numbers, the result is the corresponding range value. So this you could think of as an x, and then once you plug it in, the output is the y. Okay, so that's what we're going to do. We're just going to evaluate the functions. So let me clip this one so we can get back on track. Where do I want to put this one? What is this number? 15? Guess I'll put it here. All right. So we're getting back to some pretty straightforward stuff here. So let's write this out. 15 dot A. Okay? And let's say if f of x equals negative 4x minus 7, what is f of 3? Okay. So the way we would evaluate that is to say f of 3 equals negative 4, open parentheses, 3, close parentheses, minus 7. Okay, so f of 3 equals negative 4 times 3 is negative 12 minus 7. And negative 12 minus 7 is the same thing as 12 plus 7. And 2 plus 7 is 9, and 1 plus 0 is 1. So it's negative 19. So f of 3 equals negative 19. that is when x is 3, y is negative 19. Okay, that's what we meant by the domain mapping onto the range in our definitions from before. When the input is 3, the output is negative 19. So that's A. Now 15.B. Again, if f of x equals negative 4x minus 7, what is f of negative 7? Okay, so we'll say f of negative 7 equals negative 4, open parentheses, negative 7, close parentheses, minus 7. So f of negative 7 equals negative 4 times negative 7. Two negatives multiplied together make a positive, and 4 times 7 is 28. So this is positive 28 minus 7. So f of negative 7 equals 21. That is when x is negative 7, y is 21. Let's look at the two numbers here. So when x was 3, y was negative 19. So 3 comma negative 19. What quadrant is that? Where is the x positive and the y negative? This is Q4, right? The bottom right corner, the bottom right section, the x is positive and the y is negative. And then here we have negative 7, comma, positive 21. So where is the x negative and the y positive? Well, it's counterclockwise, right? The coordinate plane starts at quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And the trick is, this is positive comma positive, negative comma positive, negative comma negative, positive comma negative. This is the way to remember. And so we can actually make an educated guess about because this is a linear function, it's a straight line. So we can guess how this line looks. Negative 7 comma 21 is somewhere over here. And then 3 comma negative 19 is somewhere down here. So the line is going from left to right, it's going down. Okay, something like that. We could easily compute the equation. This is x1, y1, x2, y2. We're not going to. We could compute the slope, which is y2 minus y1 over x2 minus x1, and then we could plug that into the slope, or the point slope form, which is y minus y1 equals m for slope, open parentheses, x minus x1, and we could actually create a slope-intercept form equation of the line, which will give us the slope and the y-intercept, and then we could actually draw a graph and actually plot points and graph it. Okay? So we have a ton of information just from those two questions. But for the purposes of this question, f of 3 equals negative 19 and f of negative 7 equals 21. Okay, so negative 19 and 21. Let's go back up here. And we'll say f of 3 equals negative 19. That's for A. And then for B, f of negative 7 equals 21. Okay? All right, now you got to be real careful here because you're dealing with a quadratic equation. So let's copy that, and then we'll talk about why that makes things more complicated. See, the real key thing there is that in a linear equation, like we had here, the domain and the range are all real numbers. So this function is defined for every real number. But in a quadratic, it's not the range. The domain is defined for all real numbers, but the range is not defined for all real numbers. There's going to be a vertex. So this right here tells you that this thing is going to look like this. Okay, it's a horseshoe pointing down. So it's going to have a top. Okay, that's called the vertex. And beyond that point, there are no defined range values. Okay? So the range has an upper limit in this particular function. And you can tell that by the leading coefficient of the quadratic term. If that is negative, then the shape is this. Okay? If it's positive, the shape is this, and so we know that it's going to have a lower limit. Okay, so I copied it, and let's go to number 16. We'll put it here. Did I copy it? I thought I did. Yeah. Okay. So here we go with 16. Dot A. If f of x equals negative 3 x squared minus 2x plus 1 here's a question I'll ask. What y value, or what f of x value, or what output value, or what range value, okay, or what dependent value results when the function is evaluated at -4. Okay, it's not just as simple as plugging it in. You have to think about what is happening, right? So where does that -4 map on the y-axis? Or what y value does that x value map to? Does it map to an x value, a y value, right? So let's evaluate it. Let's say f of -4 so we're already on the left side, right? We're either in quadrant 2 or quadrant 3 on the x. So we want to know, where is the y value that corresponds to that horizontal domain input independent value of -4. So that equals -3 open parentheses -4 close parentheses squared minus 2x plus, well, I just messed up, minus 2 open parentheses 4 -4 close parentheses plus 1. Okay, so f of -4 equals, and now you write the -3 because you're not done with this. You have to do this first. You have to square -4 before you can multiply by -3. So the negative squared is always positive. So -4 times -4 is positive 16. So you have -3 open parentheses 16. And now there's always confusion about what to do here with this minus sign. So I always say, don't write it that way. Instead, write it like this: plus open parentheses -2 close parentheses open parentheses -4 close parentheses plus 1. And that makes it super clear what you're doing, right? If you get this into your mind, it's really clear. There is no such thing as subtraction. There's only the addition of negative numbers. Okay, so you put the plus sign in there, and then you wrap that negative symbol, and then you know, okay, I'm going to multiply -2 times -4. All right, so f of -4 equals -3 times 16. So we need to do 3 times 16 in side work. So we put 16 here and 3 here. And 6 times 3 is 18. Carry the 1. 1 times 3 is 3. 3 plus 1 is 4. So 16 times 3 is 48. But remember, it's negative 48. So we have negative 48 and then negative 2 times negative 4 is positive 8. So plus 8 plus 1. It might be helpful to do this first. What is 8 plus 1? 9. Okay? So f of negative 4 equals negative 48 plus 9. Now the way you find that out is you take 48 and you subtract 9. You can't take 9 from 8, so you have to borrow from the 4. And so the way you do that is you subtract 1, and that becomes a 3. And then you add 10 to the 8, and this becomes 18. So 18 minus 9 is 9. And then 3 minus 0 is 3. But it's negative. So that's negative 39. So f of negative 4 equals negative 39. Okay, and so what that means is that when x is negative 4, y is negative 39. So our coordinate pair would be negative 4, comma, negative 39. This is the domain value, and this is the associated corresponding range value. And that puts us in Q3, right? Now let's look at f of 0. So that's 16 dot b. If f of x equals negative 3x squared minus 2x plus 1, what output corresponds to the input of 0. See, the whole thing is a question. And so we need to evaluate negative 3x squared minus 2x plus 1 at 0. 0 is the input. 0 is the domain. And so we want to find out what is the associated range value or output value that corresponds to 0. And this happens to be the y-intercept, okay? And there's a trick. I mean, we're going to do the math, but there's a trick. The way that a quadratic function is written this is a little trick. The general form or standard form of a quadratic function is f of x equals ax squared plus bx plus c. And the c value, it can be positive or negative, okay? The c value is the y-intercept. So if your quadratic function is written in standard form, then all you have to do is look at the last number. That's all by itself, and that's the output value when the input value is 0, because that's the definition of the y-intercept. When x is 0, whatever the associated y value is the y-intercept, right? So it's 0, comma, whatever. And that number would be 1. So our prediction when we evaluate this function at 0 is that it will result in 1. But we have to show the work. We can't just assert that, okay? So we think it's 1. We think it's 0, comma 1, right? So let's evaluate it. F of 0 equals -3, open parentheses, 0, close parentheses, squared, minus 2, open parentheses, 0, close parentheses, plus 1. And so this is where it's really helpful to write the equation like this. F of 0 equals -3, open parentheses, 0 squared, plus, open parentheses, -2, close parentheses, open parentheses, 0, close parentheses, plus 1. And that really sets everything into kind of stark contrast, doesn't it? So now f of 0 equals, and we take 0 and we square it, and 0 squared is 0. So we have -3 times 0 plus -2 times 0 plus 1. So f of 0 equals, now anything times 0 is 0, so -3 times 0 is 0, plus anything times 0 is 0, so -2 times 0 is 0, plus 1. And this kind of brings into focus why we call this term, or any number in an equation or function that has no letter next to it, a constant. Okay? Because it never changes. You can plug in any number for x, and that 1 will always hang out there at the end. And that's why we call that a constant, where this and this these are variables, okay? That's why we call them variables, because they change, okay? Actually, all of this will change, right? But this won't change. So f of 0 equals, remember equals means is, 1. Therefore, remember that means therefore, that symbol means therefore, when x is 0, y is 1. Okay? So you get 0, 1. And that's the y-intercept. So we don't know enough information given these 2 points. We can't plot the quadratic graph. All we really know is that there's 1 point on the graph. We know it points down. Okay, so we know that. We know it crosses the y-axis at 1. And we know that there's a defined point in quadrant 3 at -4, -39. But we have absolutely no idea. I mean, we could determine it, right? But just from those 2 points, we don't know what the range of the function is. We could determine that by finding the vertex. But that's for a different day. We can assume that the range would be -infinity up to and including the vertex. So there'd be an upper limit there. But for the limitations of this particular problem, f of -4 is -39, and f of 0 is 1. So -39 and 1. So back to 16, f of -4 equals -39, and f of 0 equals 1. Just as a final point, what I don't want to see on the test is just that number, okay? I want you to write a complete mathematical statement. The function f of x equals -3x squared minus 2x plus 1 evaluated at -4 has a corresponding output value or range value of -39, right? That's what you're really saying with this notation right here. So you need to say it because it's a complete sentence. And you could end this with a period. All right. Now we're going to do these 4 problems. And they want us to use set builder notation for domain and range. So first we decide if it's a function. So look at number 17. Just graphically, does this look like a function? I know something we can add to this relation function thing. This is something that was on the tip of my tongue and I couldn't remember. You want to put in here, there exists, this is back to number 13 here, folks. There exists a 1-to-1 relationship between inputs and outputs. Is that always true, or is that only true for linear functions? Actually, that's only true for linear functions, right? Because for quadratic functions, let me think about this for a minute. No, I don't want to write that for number 13. Never mind. I'm thinking of a case where there's a straight line, like this example, y equals 4. So for every input value, the output value is 4, right? X equals 0, y equals 4. X equals 2 million, y equals 4. X equals negative 5,249, y equals 4. So there wouldn't be a 1-to-1 relationship there. So let's leave that alone. Okay, so is this a function? So first, let's say this is a function. Okay? And we can modify that word function with the word continuous. It's a continuous function. There's no breaks. That's what this solid line represents, continuity. And these little arrowheads on the end tell us that it goes on forever and ever in all directions in both the horizontal and vertical axes, right? So the domain is negative infinity to positive infinity, and the range is negative infinity to positive infinity. But they want us to use this set builder notation, okay? So I don't know if you've ever been exposed to this set builder notation, but there are some symbols here that we need to learn about before we can write anything. So set builder notation. There are some symbols. Here are the symbols. The bracket right there, or the brace. And then there's this straight line. And then there is an open parentheses, and there's a closed parentheses. And there's obviously a closed brace. but we'll get to that in a minute. And then there's a bracket like this, open bracket, and then there's a closing bracket. Okay, so you need to learn what these symbols mean in English. So you understand what you're saying when you write set builder notation. So here's what this means. In English, this means the set of all ... Okay? This vertical line means such that. Now this parentheses symbol, the open parentheses, means does not include. Okay? So that's excluding the value that you write here. There's some number you're going to write there. It does not include that number. It's like the lower bound. And this can be for domain or range. It's like all values up to this value or down to this value, but not this value. And then this one, you would have the number here, right? And this also means does not include that number. And this would be the upper bound. There's one exception to this rule, and that's when you're using the infinity symbol. Okay, and we'll talk about that. But we might want to make a little note that for these two symbols here, negative infinity, comma, positive infinity would be written like this with the parentheses. You would not write it like this. Okay, so this is kind of like an exception to the rule. Okay, so if these parentheses means do not include, the brackets must mean does include. Okay, so let's get back to our, let's use a different color here. How about green? We'll say does include that number. And this is the lower boundary. And then here the number would be here. And this means does include that number. And this would be the upper boundary. So I don't know how extensively they want us to use these symbols, but let's go back to the problem now that we know what these symbols mean. Let's go back up here and look at number 17. So this is a function. So let's talk about the domain, and let's use the blue color to talk about domain. And domain is associated with the letter X, right? So the easiest way to write this in set builder notation is to just put open parentheses, negative infinity, comma, positive infinity, close parentheses. And I think I'll leave it there. Now, the range we'll put in green. Now the range is the f of x value slash the y value. Okay. And so in this case, it's the same as the domain. Negative infinity, comma, positive infinity. With the parentheses. Okay. Now let's look at number 18. Is this a function? Okay, does it pass the vertical line test? Yeah, it's a quadratic function. It is continuous. And these arrowheads at the end tell us that it goes on forever, moving farther and farther to the left and to the right along the x-axis forever and ever for all eternity. Okay, so let me get back to my blue. And well, first let's write this is a continuous function. Okay. And then we can write domain, which is the x values. And we said it was negative infinity to positive infinity. And then now we finally get to do something unique, which is the range. So here's a question. So remember, though, range is the f of x slash y values. Okay. This does not have an infinite range. It has a lower boundary. Okay, right here. You see that? This is the vertex. And the vertex is located at 1, negative 4. This is the x value, and this is the f of x or y value. Okay, this number right here represents the lower boundary of this function. Okay, but it is included. So how would we write the range? Go back to your symbols. On the lower boundary, do I use this symbol or this symbol? Do I use the open parenthesis symbol or the open bracket symbol? I will use the open bracket symbol to show that it does include the value, negative 4. So here I'm going to write open bracket, negative 4, comma, and then what is the maximum value? Okay, it goes up forever and ever, right? So the maximum value is positive infinity, and we use this parentheses symbol with infinity. So that's the range of this quadratic function. Now, number 19 is not a function because it violates the vertical line test pretty much everywhere. So we're going to write this is not a function. But they want us to determine the domain and range anyway, which we can do. So let's talk about the domain. So this is kind of like the quadratic function, but it's flipped. So remember, the domain is the x value, and there is a lower boundary to what x values this can be. And here it is right here. Okay. So you see there's the vertex. Where is that located? At negative 2, 4. So the important point is the negative 2. All right, that's the lowest x value that this can be, but it includes it. So we'll use the open bracket like this. Negative 2, comma, and then these little arrowheads here tell us that it goes on forever and ever in the x direction. So there's no upper limit on the x values that this can take on. There was a lower limit, but there's no upper limit. So what I would write here is I would write positive infinity, close parentheses. Okay, so now we'll talk about range. Now range is either the f of x values or the y values. And this is always tricky for students, but just like up here, I said that the domain went to the left and to the right forever and ever. over here, whoa, sorry. Over here on this one, it goes up and down forever and ever. So we would use the open parentheses, negative infinity, comma, positive infinity, close parentheses. And then finally, we're on to number 20. We're not done with the whole problem set yet, but we're on to number 20. And this is not a function, okay? It's a circle, right? It violates the vertical line test everywhere. So this is not a function. But it does have a domain and range. And we can actually identify those points. So first we'll start with the domain. Remember, the domain is the x values that this can be. So we want to look here and here. The x value here is -2, and the x value here is 6. So that's the domain, and it's including those values. So our domain will be open bracket -2, comma, +6, closing bracket. It includes all of the x values, all the real numbers, between -2 and 6, including -2 and 6. And what about the range? Now here I'm not going to use the f of x notation. I shouldn't have used it here either, because it's not a function, right? It's just y. So here the range, it's just the y values. Now there's certainly an equation for the circle. You've probably seen the equations of circles before. So there's a y value, okay? We just kind of have to find the top and the bottom of the circle, and we see that the highest y value is 2, right? And the lowest y value is -6. Notice the relationship here. So for the range, it will be open bracket, and the lower boundary would be -6, comma, and then the upper boundary would be +2. Okay? I think that's enough to say about number 20. I wonder if, I'm just curious, was that intentional or unintentional? I'm talking about this right here. there's more complications here that I see. We're not going to be able to determine exactly where these numbers are, right? They're not hitting the lattice points in the background. I don't know what that open end over there is. Was that a mistake, or did they do that on purpose? I don't know. I didn't make this review. Well, we can certainly determine if this is a function or not, right? We can determine all of this. So students often have difficulty with the straight line thing. Is this a function? It does not ever violate the vertical line test, okay? So yes, it is a function. This is a function. This is a continuous function. You know, of the form f of x equals a constant. Remember, a constant is a number. It's just a number. So in this case, we can actually write it, because we see it, it's -2. So in this case, it's -2, right? F of x equals -2. The equation of the line is y equals -2. So now let's talk about the domain and range. First, we'll talk about the domain. Which is the x values. Okay. These little arrowheads are telling us that it goes on forever and ever in all directions on the x-axis. So all the way to -infinity and all the way to +infinity on the x-axis. It takes on every single real number that you can input into the function. But the output is always the same, okay? So here we would use that open parentheses, -infinity, comma, +infinity, closing parentheses for our domain. But our range is entirely different. It's a whole different story. So range, remember range is what f of x equals, or y. So what did I say that y and f of x equaled? Right? What is the only y value? Or think about it in function form. What is the only output that's possible on this line? Here, 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 here. What's the y value? 2. -2, -2, -2, -2, -2, -2. Right? So everywhere, forever, it's always going to be -2. So the only range value is -2. So how do you write that? Well, here's how you write it. Open bracket, -2, comma, -2, closing bracket. That's how you write the range. All right, let's look at number 22. Is this a function? No, this is not a function. Not a function. And why is it not a function? Because here the x value is, or the domain value is -3. Here the domain value is -3. And here, the domain value is also -3. All right, so the x's repeat. It's not a function. This is what we call discrete. That means that the thing that we're looking at is only defined at certain points. In this case, it's only defined at 3 points. So first, let's talk about domain. There are only 3 points. And the x values for all 3 points are -3. Inclusive, right? It's -3, inclusive. So the domain, or x, is well, I'm tempted to use the correct notation here. The domain is -3, comma, -3, comma, -3, close bracket. Right. Maybe that's not necessary. I don't know. You could just write -3, comma, -3, like that. Now let's talk about the range. So we can only talk about range because it's not a function. We can only talk about range in terms of y values. So the range is actually defined only for the y values such that y is -4, 0, and 4. -4, comma, 0, comma, 4. Now, I really don't know how they want you to write that. That's how I would write it. But maybe you would do this. -4. This is like an element of this. 0 and 4. This says the set of all y such that y includes -4, comma, 0, and 4. That's what it means. And that's kind of what the second thing means as well. It just means that this picture, I don't want to call it a function, is defined only at in the range is only defined at -4, 0, and +4. And remember, we call that discrete. Okay, discrete or finite. There is a limited number of the defined points. Okay, look at this. So don't be misled by these inflection points here, or changes in direction of the graph. This is a continuous function that goes forever in both the x and y directions. Okay? These 2 points here, these are called local minimums and maximums. They don't matter when we're talking about domain and range. So this is a function. And now we can talk about domain. Remember, domain is x, and it's going to be the infinity. So open parentheses, negative infinity, comma, positive infinity, close parentheses. And now we'll talk about range, which is the same thing. It's a function, remember? So this is f of x or y. And it is also open parentheses, negative infinity, comma, close parentheses, positive infinity, close parentheses. Okay? Now let's look at number 24. They want us to use set builder notation. It's difficult to know what to do here. So we know this is not a function, right? It violates the vertical line test. It's an ellipse. I don't know about this. This is a huge question mark for me, whether that was intentional or not. But we can certainly say this is not a function. You just say not a function for sure, right? But what's got me puzzled is the domain and the range. So let's look at domain first. Domain is the x values that this can be. So we're kind of looking here. It's somewhere between -5 and -6, right? Because -5 is actually right there, and that black line goes outside of that. So it's beyond -5, but it's not to -6. And then over here, I have no clue, right? I don't know what this means. We'll go ahead and assume that it was intentional, that it's an open circle here, that it's not defined at this point. And so we will use a parentheses when we write this number down. And that number is slightly bigger than 5, but not 6. And we don't know what it is, but it's bigger than 5, because if you see, 5 would be right there. So I'm really at kind of a loss. I would say something like I would actually use an open parentheses, and I would write -6, comma, 6, close parentheses. And that's all I can say, because I can't guess. I have no clue where this is crossing the x-axis. And that might be wrong, okay? But now here, the best I can do is I can tell you that that's 1 and that's -1, right? So for my range, our upper limit is somewhere south of 2, and our lower limit is somewhere north of -2. Okay, but it's not including 2 or -2, so for the range, and I'm not going to put f of x, I'm just going to put y. For the range, we'll just put -2 as the lower bound, but it's not including -2. and then positive 2 is the upper bound, but not including positive 2. And that's why we use the parentheses. I don't know if that's right, you know. But that's weird. Number 24 is definitely strange. I find that super confusing, actually. Okay, we are down to the final two problems, and there's enough space, finally, to work them out. And we won't belabor the point, right? We're tired. You're tired. I get it. So here, for A, we'll just jump right in and evaluate f of 0 equals negative 3 times 0 minus 2. And that's going to equal 0 minus 2, which equals negative 2. Okay, so just make sure to write f of 0 over and over again. F of 0 equals negative 2. How about B? F of 4 equals negative 3 times 4 minus 2. Make sure you do your order of operations and multiply first. Negative 3 times 4 is negative 12, so f of 4 equals negative 12 minus 2. So f of 4 equals negative 14. And then C, f of negative 1 equals negative 3 times negative 1 minus 2. So f of negative 1 equals negative 3 times negative 1 is positive 3 minus 2. So f of negative 1 equals 1. All right, we just powered through that one. Now this is a quadratic. It's going to be a little bit more complex, but we'll just do it. A, they want f of 1. So that will equal negative 11, open parentheses 1, close parentheses squared, minus 5, open parentheses 1, close parentheses, plus 13. So f of 1 equals 1 squared is 1, and then 1 times negative 11 is negative 11. 1 times negative 5 is negative 5, plus 13. Now we just move from left to right, it doesn't matter. So f of 1 equals negative 11, minus 5 is negative 16, plus 13. So f of 1 equals negative 3. Okay, that's A, and here's B. They want f of negative 1. So f of negative 1 equals negative 11, negative 1 squared, minus 5 times negative 1, plus 13. So f of negative 1 equals, now negative 1 squared is 1, 1 times negative 11 is negative 11. Negative 5 times negative 1 is positive 5, plus 13. So f of negative 1 equals negative 11 plus 5 is negative 6, plus 13. So f of negative 1 equals positive 7. 13 minus 6 is 7, right? Yep. And finally, C, f of negative 4. Okay, so this one will actually take some work. So that's going to be negative 11, open parentheses, negative 4 squared, minus 5 times negative 4, plus 13. So f of -4 equals, now you have to square -4, which would be 16. That's -11 times positive 16. And here I'm going to use plus 20, right? -5 times -4 is positive 20 plus 13. So the only thing I don't know is, what is 16 times 11? Six, 1, 6, 1, 6, 7, 176. Is that right? 176. So that would be a -176. So f of -4 equals -176. And then 20 plus 13 is 33 plus 33. It's basically like a subtraction problem. We just subtract out. Here, let me stop being so careless here. Let me just write 176 and then subtract 33. That's 3, 4, 1, negative. So this is f of -4 equals -143. Okay? And we are done with the review. Finally. At the end of the review, I always like to zoom out and show all the work that we did, just so we can kind of marvel at our endurance. Just look at that. Look at all that. That is crazy. And then I'll scan the review from top to bottom, just so you can make sure that you've got everything done. All right. I'm just going to slowly scan. Check your work. I see on number 11 I didn't put what it equals. I better fix that. See, yeah, we're glad we checked, didn't we? It was a good thing we checked. Let's go find 11. Where did that go? It was -5. Okay. See, we checked our work. Good thing. Okay. So let me get back to where I was just scanning now. Now, as we conclude this video, I need to thank you, okay? Because there's two types of people. Well, there's two types of students. There are definitely going to be students who cheat with this video. It happens. Guys, I've been doing this a long time. There are going to be students that just literally scan to the end, okay, and write it all down, okay? There are going to be students that just put on their earphones and put me on mute. and kind of scroll through the video or hit the time codes and then scroll to where the answer is shown, and then they write down everything they see. Not taking the time to listen and learn and critically listen and stop the video and try it yourself and then get confused and go back and listen to it again. Okay. And then there's that other type of student. There's the type of student that put in some significant time with this material and turns in something to me that looks a lot like what I've written here. Now, I don't know if you've been keeping track of the time codes, but I started working on this last night, I think after 10:30, sometime around 10:30, maybe it was 11 when I started recording. You'll see in the first time code of the video when it started. And I have been awake nonstop, okay? It hasn't taken me, so that let's say it was at 11 o'clock. So 12 hours would be 11 a.m. 13 hours would be noon. 14 hours would be 1. So almost 15 hours of continuous time working on this. Now, I took breaks. Okay, and there was a reason that I took breaks. I had to take breaks because otherwise I would have gone insane, right? This was just a lot of work. But I also had to take breaks due to technical reasons. This computer will overheat and freeze, and if it happens to freeze while I'm in the middle of a recording and just like goes to the blue screen and shuts down on me, I lose the recording. So this video that you're watching right now is actually a composite of something like 20 or 30 different videos. I had to start and stop and start and stop, and every time I had to stop recording, I had to like put the computer to sleep until I heard the processor wind down, and then I had to wait for the back of the computer to cool down. So I knew that the processor had cooled down, and then I would turn it back on and start recording again. And sometimes that would be a 10-minute break. Sometimes it would be a 2-minute break. Then I took the break to record the guitar, right? That was like an hour and a half. That was my longest break. But yeah, more or less, I've been working on this for like 15 hours. And that's only fair. I think that's only fair to you because I missed, the first week and a half of school, and here you're about to be tested over this material. And what I've tried to do in this video, the reason this video is so long, and the reason that I went into so much depth on every question to the point of like excruciating detail, was because I was trying to both teach you at the same time I was helping you with the review, right? I try to combine the teaching that you missed from me with the review. So if you really paid attention and watched this whole video, you got caught up with what I would have taught you had I been in school from day one. Okay? You would be all caught up. And I can almost guarantee you that if you followed everything I did in this video, you will make an A on the test. Right? If the test looks anything like the review, then you will make an A on the test if you really did sink yourself into this video. Okay? If you didn't, and you just copied the answers, or you just, whatever, you just blew through it, you didn't pay attention at all, then I kept my promise, right? My promise that I made to all of you was, I promise that I will record a complete and full solutions video to the test review with full explanations for everything. And I think that nobody will doubt that I gave a complete explanation for everything, probably too much. So I'm very proud of you. I'm very honored and thankful to be your teacher. And I really, really hope this was helpful to you. And I mean that because I just spent the last 15 hours working on it, and I'm not even done yet, right? So when you watch this video, there will have been an additional 2 or 3 hours put into it in this program down here, Camtasia. Okay, that's the video editor. I have to systematically import all 30 or 40 of those individual videos and then stitch them together in the video editor in order, okay, and then render the video out, which is going to take many, many hours. And then after that's over, I've got to upload it to YouTube, and then I have to wait for it to upload and process. And once it processes and passes all the checks, the suitability checks for the age and all that stuff, then I have to go and watch the video, okay, and pause every time I get to a new number and create a time code so that you have that table of contents thing that they put in the YouTube videos. And I'll pin the time codes in the description and in the top comment. I'll pin it in a comment so that you can just click and you should just be able to go directly to the number that you want to see. Okay? All right, guys. Well, that concludes this test 1.1 review for Algebra 2. Thank you so much for watching.